The nature of dark matter and dark energy. Let's start our journey with a simple question. What is the universe made of? If you were to list everything you know, stars, planets, galaxies, even the air we breathe, you'd account for less than 5% of the cosmos. The rest? A mysterious duo, dark matter and dark energy. Together they make up 95% of the universe, yet they remain invisible, undetectable, and utterly enigmatic. The story of dark matter begins in the 1930s with a Swiss astronomer named Fritz Zwicky. While studying the Coma cluster of galaxies, he noticed something strange. The galaxies were moving so fast that, according to the laws of gravity, they should have flung themselves apart, but they didn't. Zwicky proposed an invisible force was holding them together, a missing mass he called dunkle materie, or dark matter. For decades, his idea was dismissed. But in the 1970s, astronomer Vera Rubin revived the mystery. She observed that stars at the edges of galaxies rotated just as quickly as those near the center. According to Newton's laws, this shouldn't happen. The outer stars should slow down, like planets farther from the sun. Rubin concluded that galaxies must be embedded in vast halos of unseen matter, its gravity keeping the stars in motion. Dark matter had announced itself. But what is it? Dark matter is not like ordinary matter. It doesn't emit, absorb, or reflect light. It passes through you right now, like a ghost without a trace. Yet its gravitational pull shapes the cosmos. Imagine the universe as a grand cathedral. The stars and galaxies are the stained glass and vaulted arches, visible, beautiful, but fragile. Dark matter is the unseen scaffolding, the iron and stone holding it all together. Without it, galaxies would fly apart, and the universe, as we know it, wouldn't exist. But how do we study something invisible? Scientists use clever tricks. One method is gravitational lensing. When light from a distant galaxy passes through a cluster of dark matter, the invisible mass bends the light like a lens, distorting the galaxy's image. By mapping these distortions, we can trace dark matter's distribution. Another clue comes from the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in this ancient light reveal how matter clumped together in the early universe. The pattern matches simulations only if dark matter exists, acting as a gravitational glue for the first galaxies. So what could dark matter be made of? The leading candidate is WIMPs, weakly interacting massive particles. These hypothetical particles rarely interact with normal matter, except through gravity. Yet decades of searches in underground labs, like the Large Hadron Collider and the cryogenic dark matter experiment, have found nothing. Alternative theories abound. Could dark matter be axions, ultralight particles predicted by quantum physics, or primordial black holes formed in the chaos of the Big Bang? Some even suggest our understanding of gravity is wrong, a theory called modified Newtonian dynamics, but most scientists still bet on particles we've yet to discover. While dark matter pulls the universe together, dark energy pushes it apart. This discovery came as a shock. In 1998, two teams of astronomers set out to measure the universe's expansion using distant supernovae. They expected to find the expansion slowing down as gravity pulled galaxies back. Instead, they found it was speeding up. The universe wasn't just expanding, it was accelerating, as if an invisible force was stretching space-time itself. This force was dubbed dark energy, and it's even stranger than dark matter. It makes up 68% of the universe and appears to be uniform, permeating every corner of space. But what is it? Einstein might have predicted it. In 1917, he introduced the cosmological constant, a fudge factor in his equations to keep the universe static. When Edwin Hubble later proved the universe was expanding, Einstein called it his greatest blunder. But in 1998, the cosmological constant made a comeback. Today, it's the leading explanation for dark energy, a property of empty space itself, generating repulsive gravity. Yet problems remain. Quantum physics predicts the energy of empty space, vacuum energy, should be astronomically stronger than what we observe. This mismatch is off by a factor of 10 to the power of 120, a number so large it's been called the worst theoretical prediction in the history of physics. Alternative theories suggest dark energy isn't constant. Maybe it's a dynamic field called quintessence, evolving over time. Or perhaps our universe is colliding with another in a higher dimensional bulk, an idea from string theory. But without direct evidence, these remain speculative. The fate of the universe hinges on dark energy. If it continues to dominate, galaxies will drift apart until the cosmos becomes a cold, dark void, a heat death. If it strengthens, it could tear apart atoms in a big rip, or if it weakens, gravity might reverse the expansion in a big crunch. For now, the outcome is unknown. Dark matter and dark energy are cosmic partners in a delicate balance. In the early universe, dark matter's gravity pulled matter into galaxies and clusters. But as the universe expanded, dark energy's repulsive force grew dominant, overriding gravity's pull. This balance raises profound questions. Why did dark energy switch on billions of years after the Big Bang? Is this timing a coincidence, or is there a deeper connection between dark matter and dark energy? Some theories propose they're two sides of the same coin, a unified dark fluid with unusual properties. Others suggest we're missing a fundamental law of physics. For example, entropic gravity argues that gravity isn't a fundamental force, but an emergent effect of entropy, the tendency toward disorder. Could this explain dark matter's effects without invisible particles? Meanwhile, experiments continue. The Euclid Space Telescope, launched in 2023, maps dark matter and energy in 3D by observing billions of galaxies. The Dark Energy Spectroscopic Instrument studies the universe's expansion in unprecedented detail. And deep underground, detectors like Lux Zeppelin hunt for dark matter particles. Yet the more we learn, the stranger the universe seems. Dark matter and dark energy defy our expectations, challenging the standard model of physics. They remind us that science is not a set of answers, but a process of asking better questions. As we ponder these mysteries, we confront the limits of human knowledge. For all our technology, 95% of the universe remains hidden. It's humbling and exhilarating. Dark matter and dark energy force us to rethink reality. Are we like fish in a pond, unaware of the ocean beyond? Could there be entire dimensions or forces we've yet to perceive? Or is the universe, as Einstein said, not only stranger than we imagine, but stranger than we can imagine? Perhaps these mysteries are not obstacles, but invitations. They remind us that curiosity is endless, and the cosmos still holds wonders beyond our wildest dreams. So as you drift into relaxation, let your mind wander among the stars. And remember, the greatest discoveries lie just beyond the edge of what we know. The arrow of time. Time is the most familiar yet mysterious force in our lives. We feel it slipping through our fingers, carrying us from past to future. But why does time move forward? Why do we remember yesterday but not tomorrow? This is the enigma of the arrow of time, the one-way directionality that shapes our existence. Imagine a film reel. If you played it backward, you'd instantly notice the absurdity. Shattered glass leaping onto a table, smoke retreating into a fire, a melted ice cube refreezing. These processes are irreversible, and their asymmetry defines time's arrow. But according to the laws of physics, most microscopic interactions, like particles colliding, are perfectly reversible. So why does the macroscopic universe insist on moving forward? The answer lies in a concept called entropy, a measure of disorder. In the 19th century, physicist Ludwig Boltzmann proposed that entropy naturally increases over time, a rule now known as the second law of thermodynamics. Think of entropy as a cosmic hourglass. Once the sand pours out, it doesn't flow back. This rise in disorder gives time its direction. But here's the paradox. If the laws of physics are symmetric, why did the universe start with such low entropy to begin with? To unravel this, we must journey back to the dawn of time itself. Picture the Big Bang. The newborn universe was hot, dense, and remarkably ordered. A sea of particles almost perfectly uniform, like a pristine, unshuffled deck of cards. As the cosmos expanded and cooled, entropy began to climb. Gravity pulled matter into galaxies and stars. Nuclear fusion forged heavier elements, and life emerged on tiny planets. Each step increased disorder, yet created pockets of complexity. a paradox that still baffles scientists. Why was the early universe so ordered? This is the past hypothesis, proposed by physicist Hugh Price. It suggests the Big Bang set the initial low-entropy condition, like winding a clock spring. Once wound, the spring unwinds, driving time's arrow forward. But this raises deeper questions. Was the Big Bang a unique event? Or could there be a mirror universe where time flows backward? In 2016, physicists Julian Barber and Tim Kozlowski explored this idea. They simulated a universe of 1,000 particles and found that entropy naturally rises away from a central low-entropy point. This implies time's arrow could flow in two directions from the Big Bang, like branches of a tree. If true, there might be a reverse universe where cause follows effect, and people grow younger. But for us, the arrow points only forward, forever separating past from future. While thermodynamics explains time's arrow, quantum mechanics complicates the story. At the quantum level, particles don't care about past or future. Equations like the Wheeler-DeWitt equation, a cornerstone of quantum gravity, suggest time might not exist fundamentally. Instead, it could emerge from deeper, timeless laws. This idea, called the problem of time, challenges our everyday experience. If time is an illusion, why do we perceive it so vividly? Some physicists, like Carlo Rovelli, propose that time emerges from quantum interactions. Imagine a crowd of people. Individually, they move randomly, but together, they create the illusion of a flowing river. Similarly, time might arise from the quantum entanglement of particles. Yet even here, entropy plays a role. In 2009, physicist Seth Lloyd argued that quantum entanglement increases entropy, creating a quantum arrow of time. Every interaction between particles, every shared photon or colliding electron, leaves a tiny imprint of irreversibility. Over eons, these imprints accumulate, weaving the fabric of time itself. Black holes, those cosmic vacuum cleaners, add another twist to time's mystery. When matter falls into a black hole, it crosses the event horizon, a point of no return. To an outside observer, time slows to a crawl for the falling object, freezing it in place. But for the object itself, time flows normally until it reaches the singularity. This duality highlights relativity's flexibility with time. Einstein showed that time is relative, stretching and compressing depending on speed and gravity. Yet even in relativity, causality is preserved. Cause always precedes effect. But what happens inside a black hole? Some theories suggest time and space swap roles, turning the singularity into a moment in time rather than a point in space. Black holes also emit Hawking radiation, slowly evaporating over eons. This process is irreversible, increasing entropy and reinforcing time's arrow. Yet when a black hole dies, does the information it consumed vanish forever? This black hole information paradox pits quantum mechanics against relativity, hinting at a deeper connection between time, entropy, and the fabric of reality. Time's arrow isn't just a cosmic phenomenon. It's woven into our consciousness. We perceive time as a flow because our brains create a narrative of cause and effect. Memories anchor us to the past, while anticipation pulls us toward the future. But what if this is an illusion? Neurologists like David Eagleman argue that our brains construct time retrospectively. When you touch a hot stove, pain seems instantaneous, but it actually takes milliseconds for signals to reach your brain. Your mind edits the timeline, creating a seamless story. This post-diction suggests that the now we experience is a carefully crafted illusion. Philosophers have long debated time's nature. St. Augustine wrote, "What then is time? If no one asks me, I know. If I wish to explain it to one who asks, I know not." Modern science hasn't fully resolved his dilemma. Is time a fundamental property of the universe, or a mental construct? The answer may lie in the interplay between entropy and consciousness. What does the future hold for time's arrow? If entropy keeps increasing, the universe may face a heat death, a state of maximum disorder where stars burn out, black holes evaporate, and all activity ceases. Time would lose meaning in this frozen, eternal equilibrium. But some theories suggest a cyclical cosmos. In conformal cyclic cosmology, proposed by Roger Penrose, the end of one universe becomes the Big Bang of another. entropy resets, and time's arrow flips. Similarly, the multiverse hypothesis imagines countless universes with different arrows of time. Even stranger is the quantum resurrection idea. In an infinitely expanding universe, quantum fluctuations could eventually reconfigure particles into an identical copy of today's world. You'd wake up, unaware eons had passed. A cosmic déjà vu. These ideas are speculative, but they remind us that time's arrow may not be absolute. It could be a local phenomenon, unique to our corner of reality. As we ponder time's mysteries, we confront our place in the cosmos. Time gives life meaning. It allows growth, change, and stories. Yet it also brings loss and impermanence. The poet T.S. Eliot wrote, "Time present and time past are both perhaps present in time future." Science and philosophy converge here. The arrow of time is both a physical fact and a narrative tool. It lets us distinguish memory from hope, regret from anticipation. Without it, existence would be a static painting, frozen in an eternal now. Perhaps time's arrow is a gift. It grants us the chance to learn, love, and imagine. As you drift into relaxation, consider this. Every moment is a bridge between the ordered past and the uncertain future. And in that uncertainty lies the beauty of being alive. The Fermi Paradox. Imagine standing on a quiet beach at night, gazing at the stars. The universe stretches before you, vast and infinite. With billions of galaxies, each containing billions of stars and planets, it feels inevitable that life, intelligent life, exists elsewhere. Yet, as you listen, the cosmos is silent. No signals, no messages, no signs of civilizations. This is the Fermi Paradox, the contradiction between the high probability of extraterrestrial life and the lack of evidence for it. The paradox takes its name from physicist Enrico Fermi, who famously asked during a casual lunch conversation in 1950, "Where is everybody?" His question was simple but profound. If the universe is so vast and ancient, why haven't we encountered other intelligent beings? To understand the paradox, let's start with the numbers. The Milky Way alone contains over 100 billion stars, many with planets in the habitable zone, the region where liquid water, and thus life, could exist. Even if only a tiny fraction of these planets develop intelligent life, the galaxy should be teeming with civilizations. And yet, we see nothing. Why? In 1961, astronomer Frank Drake tried to quantify the likelihood of intelligent life. His Drake equation is a series of factors multiplied together: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, and so on. While the equation doesn't give a definitive answer, it highlights the vast possibilities. For example, if even 1% of habitable planets develop intelligent life, there should be millions of civilizations in the Milky Way. So where are they? This question has sparked countless theories, each offering a possible explanation for the Great Silence. One of the most unsettling explanations is the Great Filter, a hypothetical barrier that prevents life from reaching interstellar communication. The filter could lie in our past or our future. If it's in our past, it means the emergence of intelligent life is extraordinarily rare. Perhaps the leap from simple cells to complex organisms is a fluke, or maybe civilizations self-destruct before they can explore the stars. If this is true, we might be alone, or among the very few. If the filter lies ahead, it means our future holds a catastrophic event. Climate change, nuclear war, or runaway artificial intelligence could doom civilizations before they spread beyond their home planets. This idea is both a warning and a call to action, urging us to safeguard our future. Another intriguing idea is the zoo hypothesis. Imagine Earth as a nature preserve, carefully observed by advanced civilizations who choose not to interfere. They might see us as primitive, like ants in an anthill, or they might follow a prime directive, a rule against contacting less developed species. This hypothesis raises philosophical questions. If we are being watched, what does it mean for our sense of purpose? Are we experiments, or are we simply too insignificant to notice? The silence of the cosmos could be a deliberate choice, a cosmic game of hide and seek. Perhaps Earth is special. The rare Earth hypothesis argues that complex life requires an unlikely combination of factors: a stable star, a large moon to stabilize the planet's tilt, plate tectonics to recycle nutrients, and a magnetic field to shield against radiation. If true, Earth might be a cosmic oasis, a rare jewel in a barren universe. This idea is both humbling and awe-inspiring. It suggests that life, as we know it, is a fragile and precious phenomenon. In Liu Cixin's science fiction novel The Dark Forest, the universe is a dangerous place. Civilizations hide in the shadows, afraid to reveal themselves. Contact could mean annihilation, as advanced species might see others as threats. This theory, while fictional, offers a chilling explanation for the Fermi Paradox. If civilizations are inherently distrustful, the universe might be a silent battlefield, with everyone too afraid to speak. It's a sobering reminder of the darker aspects of intelligence and survival. Perhaps advanced civilizations have evolved beyond our comprehension. They might exist in dimensions we can't perceive, or they might have transcended physical forms, becoming pure energy or information. This idea, known as the transcendence hypothesis, suggests that the universe is full of life, but it's invisible to us. We might be like ants in a forest, unaware of the humans walking above. The silence of the cosmos could be a sign of our own limitations, a reminder of how much we have yet to learn. Another radical idea is the simulation argument, proposed by philosopher Nick Bostrom. It suggests that we might be living in a computer simulation created by an advanced civilization. If true, the Fermi Paradox could have a simple explanation. The simulators haven't programmed other civilizations into our reality. This theory blurs the line between science and philosophy, challenging our understanding of existence itself. Are we alone because we're not real? Or is the simulation designed to isolate us, like characters in a cosmic video game? Perhaps we're simply too early or too late. The universe is 13.8 billion years old, but intelligent life might be a fleeting phenomenon. Civilizations could rise and fall in cosmic blinks, missing each other by millions of years. Alternatively, we might be among the first. The early universe was too chaotic for life, and only now are conditions becoming favorable. If true, we could be pioneers, destined to spread life across the stars. Despite the silence, we keep searching. Projects like SETI search for extraterrestrial intelligence, scan the skies for signals, while missions to Mars and Europa hunt for microbial life. Each discovery, or lack thereof, brings us closer to understanding our place in the universe. The Fermi Paradox is more than a scientific question. It's a mirror reflecting our hopes, fears, and curiosity. It reminds us that the universe is vast and mysterious, full of possibilities we can't yet imagine. As we ponder the Fermi Paradox, we confront the limits of our knowledge. The silence of the cosmos is both a mystery and an invitation to explore, to wonder, and to dream. Perhaps the answer lies not in finding others, but in understanding ourselves. The universe is a canvas, and we are the artists, painting our story across the stars. Whether we are alone or part of a cosmic community, the journey itself is what matters. So as you drift into relaxation, let your mind wander among the stars. Imagine the possibilities, the civilizations waiting to be discovered, and the mysteries yet to unfold. The universe is vast, and the story is far from over. The mystery of consciousness. Close your eyes for a moment and listen to your thoughts. Feel the sensations of your body, the rhythm of your breath. This inner world, your awareness of yourself and your surroundings, is what we call consciousness. It's the most intimate and mysterious aspect of our existence. Yet, despite centuries of inquiry, we still don't fully understand what it is or how it arises. Consciousness is both universal and unique. Every person experiences it, yet no two experiences are exactly alike. Your perception of the color blue, the taste of chocolate, or the sound of rain is yours alone. This subjective quality, known as qualia, is at the heart of the mystery. How can something so personal and intangible emerge from the physical processes of the brain? This question has puzzled philosophers and scientists for millennia. René Descartes famously declared, "Cogito, ergo sum." I think, therefore I am. He saw consciousness as proof of existence, a beacon of certainty in a world of doubt. But while Descartes affirmed its reality, he couldn't explain its origin. Today we're still searching for answers. In the 1990s, philosopher David Chalmers coined the term the hard problem to describe the central mystery of consciousness. The problem is this: how and why do physical processes in the brain give rise to subjective experience? Consider your brain for a moment. It's a 3-pound organ made of neurons, electrical impulses, and chemicals. When you see a sunset, neurons fire in your visual cortex. When you hear music, sound waves trigger activity in your auditory cortex. But why should these processes feel like anything at all? Why isn't the brain just a silent, unfeeling machine? This question separates consciousness from other scientific challenges. We can explain how the brain processes information, but not how it generates the experience of being. As philosopher Thomas Nagel put it, there's something it is like to be a conscious being. This something remains elusive, a puzzle that defies easy explanation. Despite the mystery, scientists and philosophers have proposed many theories to explain consciousness. Each offers a unique perspective, but none have fully solved the puzzle. One leading idea is integrated information theory, developed by neuroscientist Giulio Tononi. Integrated information theory suggests that consciousness arises from the integration of information in the brain. The more interconnected and complex the information, the richer the conscious experience. This theory even proposes a measure called phi, which quantifies the level of consciousness in a system. Another prominent theory is the global workspace theory, proposed by Bernard Bars. Imagine the brain as a theater. Consciousness is the spotlight, illuminating certain thoughts and sensations on the stage of awareness. According to global workspace theory, consciousness emerges when information is broadcast across the brain, allowing different regions to work together. Then there's panpsychism, a radical idea that consciousness is a fundamental property of the universe, like mass or charge. In this view, even atoms and particles have a tiny spark of awareness. When combined in complex systems like brains, these sparks give rise to full-blown consciousness. Other theories, like higher-order thought and predictive processing, focus on the brain's ability to reflect on its own states or predict incoming sensory data. Each theory offers a piece of the puzzle, but the full picture remains out of reach. While philosophers debate the nature of consciousness, neuroscientists are mapping its physical basis. Using tools like fMRI and EEG, they've identified brain regions and networks associated with awareness. One key area is the prefrontal cortex, responsible for higher-order thinking and self-awareness. Damage to this region can alter personality or even erase the sense of self, as seen in cases like Phineas Gage, a 19th-century railroad worker who survived a rod piercing his skull, but lost his ability to plan or control impulses. Another critical network is the default mode network, DMN, active when we daydream or reflect on ourselves. The DMN is thought to play a role in creating the narrative of our lives, the story of me that defines our identity. Yet even with these insights, we don't know how these regions produce consciousness. Is it a specific pattern of neural activity, a particular frequency of brain waves, or something beyond our current understanding? The brain remains a labyrinth, and consciousness its deepest secret. To explore consciousness, scientists study altered states, dreams, meditation, psychedelics, and even near-death experiences. These states reveal the flexibility and fragility of awareness. Take dreams, for example. When we sleep, our brains create vivid worlds, blending memories, emotions, and imagination. Yet, we often don't realize we're dreaming until we wake up. This raises questions about the nature of reality. How do we know our waking life isn't just another dream? Psychedelics like LSD and psilocybin offer another window. These substances disrupt normal brain activity, leading to profound changes in perception, thought, and emotion. Users often report a sense of unity with the universe or a dissolution of the self. These experiences suggest that consciousness isn't fixed but fluid, shaped by the brain's chemistry and structure. Near-death experiences are equally fascinating. People who've come close to death often describe vivid visions, out-of-body sensations, and encounters with light or loved ones. While some attribute near-death experiences to brain activity under stress, others see them as evidence of consciousness existing beyond the body. The truth remains unknown. At the core of consciousness is the self, the I that experiences the world. But is the self real, or is it an illusion? Neuroscientist Anil Seth argues that the self is a construct, a story the brain tells to make sense of its experiences. Think of it as a dashboard, summarizing the body's state and the environment. This idea aligns with Buddhist philosophy, which sees the self as a fleeting illusion, a collection of thoughts and sensations without a permanent essence. Yet the self feels undeniably real. It's the anchor of our identity, the voice in our heads, the witness to our lives. Whether it's an illusion or a fundamental truth, the self remains one of consciousness's greatest mysteries. As we build increasingly intelligent machines, a new question arises. Can artificial intelligence become conscious? Some argue that consciousness requires biological processes, like the firing of neurons. Others believe it's a matter of complexity. If a machine's information processing is sophisticated enough, it could develop awareness. This debate raises ethical questions. If a machine were conscious, would it have rights? Would it feel pain or joy? For now, AI lacks the subjective experience that defines consciousness. But as technology advances, the line between human and machine awareness may blur, forcing us to confront what it truly means to be conscious. As we ponder the mystery of consciousness, we confront the wonder of our own existence. Consciousness is the lens through which we experience the universe, the light that gives meaning to reality. It's easy to take it for granted, to lose ourselves in the busyness of life. But when we pause and reflect, we glimpse the profound mystery at the heart of being. Why are we aware? Why does the universe give rise to minds that can ponder their own existence? These questions may never have definitive answers, but perhaps the mystery itself is the point. Consciousness invites us to wonder, to explore, and to marvel at the miracle of being alive. So as you drift into relaxation, let your mind wander through the labyrinth of awareness. Feel the rhythm of your breath, the quiet hum of your thoughts. In this moment, you are the universe experiencing itself, a fleeting, fragile, and infinitely beautiful spark of consciousness. The Multiverse Hypothesis. Imagine standing on the edge of a vast ocean, its waves stretching endlessly to the horizon. Now, imagine that ocean is the universe, not just our universe, but one of countless others, each with its own stars, planets, and perhaps even life. This is the Multiverse Hypothesis, the idea that our universe is just one of many, part of an infinite cosmic tapestry. The multiverse concept challenges our understanding of reality. For centuries, we've thought of the universe as everything that exists, a single, unified expanse of space and time. But modern physics suggests this might be just the beginning. The Multiverse Hypothesis proposes that our universe is one bubble in a frothy sea of universes, each with its own laws of physics, its own history, and its own destiny. Where did this idea come from, and what evidence, if any, supports it? Let's dive into the science and philosophy behind the multiverse. The multiverse hypothesis has its roots in cosmic inflation, a theory developed in the 1980s to explain the uniformity of the universe. According to inflation, the early universe underwent a rapid expansion, smoothing out irregularities and setting the stage for the cosmos we see today. But inflation doesn't stop there. Some physicists, like André Linde, propose that inflation is eternal, creating an endless cascade of universes. In this view, our universe is just one pocket, in an ever-expanding multiverse. Each pocket has its own Big Bang, its own physical constants, and its own unique properties. This idea is both exhilarating and humbling. It suggests that the universe is far larger and stranger than we can imagine, with infinite possibilities waiting to be explored. While cosmic inflation gives us one version of the multiverse, quantum mechanics offers another. According to the many worlds interpretation, every quantum event spawns a new universe. Here's how it works. At the quantum level, particles exist in a state of superposition, meaning they can be in multiple states at once. When we observe them, they collapse into a single state. But the many worlds interpretation suggests there's no collapse. Instead, every possible outcome happens, each in its own universe. For example, if you flip a coin, one universe sees it land heads, while another sees tails. Over time, these branching paths create an infinite web of realities, each slightly different from the next. In one universe, you might be a musician. In another, an astronaut. The possibilities are endless. This idea raises profound questions about free will and identity. Are we the architects of our lives? Or are we just one version of ourselves, living out a single thread in an infinite tapestry? String theory, a candidate for the theory of everything, adds another layer to the multiverse hypothesis. According to string theory, the fundamental building blocks of the universe are tiny, vibrating strings. These strings exist in a higher dimensional space, with our universe occupying just 3 of those dimensions. But string theory doesn't predict a single universe. Instead, it suggests a landscape of universes, each with its own configuration of dimensions and physical constants. Some universes might have stronger gravity, while others might have no stars at all. This landscape is vast and varied, offering a potential explanation for why our universe has the properties it does. If every possible configuration exists somewhere, it's no surprise that we find ourselves in a universe capable of supporting life. This idea, known as the anthropic principle, suggests that our existence shapes our perception of reality. Another version of the multiverse comes from brain cosmology, an offshoot of string theory. In this view, our universe is a 3-dimensional brain floating in a higher dimensional space called the bulk. Other brains might exist nearby, each hosting its own universe. These brains could collide, creating new Big Bangs and new universes. Some physicists even suggest that the Big Bang itself was the result of such a collision. If true, our universe might be just one of many, separated by dimensions we can't perceive. This idea is both fascinating and frustrating. If other universes exist in higher dimensions, how could we ever detect them? For now, they remain beyond our reach, hidden in the folds of reality. Some physicists, like Max Tegmark, take the multiverse idea even further. Tegmark proposes a mathematical multiverse, where every mathematically possible universe exists. In this view, reality isn't just described by mathematics, it is mathematics. This idea blurs the line between physics and philosophy. If every mathematical structure corresponds to a real universe, then the multiverse is not just infinite but also infinitely diverse. Some universes might be simple, governed by basic equations, while others might be unimaginably complex. The mathematical multiverse challenges our understanding of existence. Is reality fundamentally mathematical? And if so, what does that mean for our place in the cosmos? While the multiverse hypothesis is compelling, it's also controversial. Critics argue that it's untestable, a scientific idea without evidence. After all, if other universes are beyond our reach, how can we ever know they exist? But some scientists are looking for clues. One possibility is cosmic microwave background radiation, the afterglow of the Big Bang. If our universe collided with another, it might leave an imprint in the cosmic microwave background, like a bruise on the fabric of space-time. Another approach involves studying the fine-tuning of physical constants. If the multiverse exists, it could explain why our universe seems so perfectly suited for life. The constants of nature, like the strength of gravity or the mass of electrons, might vary across universes, with ours being one of the rare ones capable of supporting complexity. For now, the evidence is indirect and speculative, but as our tools and theories advance, we might one day find proof of the multiverse, or rule it out entirely. The multiverse hypothesis isn't just a scientific idea, it's a philosophical one. It challenges our understanding of reality, identity, and meaning. If the multiverse exists, are we special, or are we just one of countless versions of ourselves? Does our universe have a purpose, or is it a random bubble in an infinite sea? These questions have no easy answers, but they invite us to think deeply about our place in the cosmos. The multiverse also raises questions about free will and destiny. If every possible outcome happens somewhere, Are our choices meaningful? Or are we just following a script written by the laws of physics? Ultimately, the multiverse hypothesis reminds us of the vastness and mystery of existence. It invites us to wonder, to explore, and to dream. Whether or not other universes exist, the idea of the multiverse expands our imagination, opening doors to infinite possibilities. As we come to the end of our journey through the multiverse, let's take a moment to reflect. The multiverse hypothesis is a reminder that reality is far stranger and more beautiful than we can imagine. It challenges us to think beyond the limits of our experience, to embrace the unknown, and to marvel at the infinite tapestry of existence. So, as we continue to our next unsolved science mystery, let your mind wander through the infinite possibilities of the multiverse. Imagine the stars, the galaxies, and the countless worlds waiting to be discovered. Whether or not other universes exist, the idea of the multiverse invites us to dream and to wonder what lies beyond the horizon of our reality. The black hole information paradox. Imagine throwing a book into a fire. As the pages burn, the information they contain, the words, the stories, the ideas, seems lost forever. But in reality, the information isn't truly gone. It's just transformed, encoded in the smoke, the ash, and the heat. If you could gather every particle and analyze it perfectly, you could, in theory, reconstruct the book. Now, imagine throwing that book into a black hole. According to Einstein's theory of general relativity, the book would be lost forever, crushed into the singularity at the black hole's center. But quantum mechanics, the other pillar of modern physics, tells us that information can never be destroyed. This contradiction is the heart of the black hole information paradox, one of the most profound mysteries in science. The paradox forces us to confront the limits of our understanding. It pits two of the most successful theories in physics, general relativity and quantum mechanics, against each other, revealing a deep rift in our knowledge of the universe. Let's explore this cosmic enigma and the ideas that seek to resolve it. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse under their own weight, creating a singularity, a point of infinite density at their core. Surrounding the singularity is the event horizon, the boundary beyond which escape is impossible. For decades, black holes were thought to be simple objects, defined only by their mass, charge, and spin. This idea, known as the no-hair theorem, suggests that all other information about what falls into a black hole is lost. If you throw a book, a chair, or a planet into a black hole, the result is the same, a featureless, informationless void. But this simplicity clashes with quantum mechanics, which insists that information must be preserved. In the quantum world, every particle, every interaction, leaves a trace. The idea that black holes erase information threatens the foundation of quantum theory, creating a paradox that has puzzled physicists for decades. In 1974, Stephen Hawking made a groundbreaking discovery. Black holes aren't completely black. Due to quantum effects near the event horizon, they emit radiation, now known as Hawking radiation. Over time, this radiation causes black holes to lose mass and eventually evaporate. At first, this seemed like a solution to the paradox. If black holes emit radiation, perhaps the information about what fell into them is encoded in that radiation. But Hawking's calculations suggested otherwise. The radiation appeared to be random, carrying no information about the black hole's contents. If true, the information would be lost forever, violating quantum mechanics. This conclusion shocked the physics community. It suggested that our understanding of the universe was fundamentally flawed, sparking a decades-long quest to resolve the paradox. One of the most promising ideas to resolve the paradox is the holographic principle, proposed by Gerard 't Hooft and Leonard Susskind in the 1990s. This principle suggests that all the information contained within a volume of space can be encoded on its boundary, like a hologram. For a black hole, this means the information about everything that falls into it could be stored on its event horizon. As the black hole evaporates, this information could be released in the Hawking radiation, preserving the integrity of quantum mechanics. The holographic principle is deeply counterintuitive. It suggests that our three-dimensional reality might be a projection of information encoded on a two-dimensional surface. If true, it would revolutionize our understanding of space, time, and information. In 2012, physicists Ahmed Almhairi, Donald Marolf, Joe Polchinski, and James Sully proposed a radical idea: the firewall paradox. They argued that if information is preserved at the event horizon, it would require an intense wall of energy, a firewall, that would incinerate anything falling into the black hole. This idea challenges our understanding of black holes. According to general relativity, crossing the event horizon should be uneventful, like passing through an invisible boundary. But the firewall paradox suggests that the event horizon is a place of extreme violence, contradicting Einstein's theory. The firewall paradox reignited the debate over the information paradox, forcing physicists to rethink their assumptions. Is the event horizon a peaceful boundary or a fiery wall? The answer remains elusive. Another intriguing idea is the ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind. This conjecture suggests a deep connection between two seemingly unrelated concepts: Einstein-Rosen bridges, wormholes, and entangled particles, EPR pairs. In this view, particles falling into a black hole could be connected to the Hawking radiation via quantum entanglement, forming a wormhole that preserves information. This idea blurs the line between space and quantum mechanics, offering a potential resolution to the paradox. The ER equals EPR conjecture is still speculative, but it highlights the creativity and ingenuity of physicists in their quest to solve the paradox. It also underscores the deep connections between seemingly unrelated phenomena in the universe. At the heart of the information paradox is the clash between general relativity and quantum mechanics. To resolve the paradox, we need a theory of quantum gravity, a framework that unites these two pillars of physics. One candidate is string theory, which posits that the fundamental building blocks of the universe are tiny vibrating strings. String theory suggests that black holes might be composed of these strings, preserving information in their structure. Another approach is loop quantum gravity, which proposes that spacetime is made of discrete loops. In this view, black holes might have a granular structure that prevents information loss. While these theories are still in development, they offer hope for a unified understanding of the universe, one that resolves the information paradox and reveals the true nature of black holes. The black hole information paradox isn't just a scientific puzzle, it's a philosophical one. It challenges our understanding of reality, information, and the nature of existence. If information is preserved, what does that mean for the fate of the universe? Could the cosmos be a vast information processing system, encoding every event in its fabric? And if so, what does that say about our place in the grand scheme of things? The paradox also raises questions about the limits of human knowledge. Are we capable of understanding the deepest mysteries of the universe? Or are there truths that will always elude us? As we ponder these questions, we're reminded of the beauty and complexity of the cosmos. The black hole information paradox is a testament to the power of curiosity, the drive to explore the unknown, and the wonder of existence itself. As we come to the end of our journey through the black hole information paradox, let's take a moment to reflect. The paradox is a reminder that the universe is far stranger and more mysterious than we can imagine. It challenges us to think beyond the limits of our understanding, to embrace the unknown, and to marvel at the infinite horizon of possibility. So as you drift into relaxation, let your mind wander through the depths of spacetime. Imagine the black holes, the wormholes, and the infinite mysteries waiting to be discovered. Whether or not we solve the paradox, the journey itself is what matters. A journey of curiosity, wonder, and endless exploration. The origins of life. Imagine standing on the shore of an ancient ocean, billions of years ago. The air is thick with volcanic gases, the sky a hazy orange. Lightning crackles above, and waves crash against rocky shores. In this chaotic, primordial world, something extraordinary happens. Life begins. But how? How did lifeless molecules come together to form the first living cells? This is one of the greatest mysteries in science, the origin of life. It's a question that bridges biology, chemistry, and physics, and it takes us to the very heart of what it means to be alive. For centuries, humans have pondered the origins of life. Ancient cultures told stories of gods and creation myths. Today, we turn to science for answers. Yet despite our advances, the exact moment when non-life became life remains shrouded in mystery. Let's explore the theories and experiments that seek to unravel this cosmic puzzle. One of the most famous ideas about the origin of life is the primordial soup theory. In the 1920s, scientists like Alexander Oparin and J.B.S. Haldane proposed that Earth's early oceans were a rich broth of organic molecules, a soup where life could emerge. In 1953, Stanley Miller and Harold Urey tested this idea with a groundbreaking experiment. They filled a flask with water, methane, ammonia, and hydrogen, gases thought to resemble Earth's early atmosphere, and sparked it with electricity to simulate lightning. After a week, they found amino acids, the building blocks of proteins, in the mixture. This experiment suggested that the ingredients for life could form naturally under the right conditions. But creating amino acids is one thing. Creating life is another. How did these molecules organize themselves into the first cells? This question leads us to the next piece of the puzzle. Today, life is built on two key molecules, DNA, which stores genetic information, and proteins, which carry out the work of the cell. But in the beginning, there might have been a simpler molecule that could do both, RNA. RNA is a versatile molecule. It can store information like DNA and catalyze reactions like proteins. This dual role has led scientists to propose the RNA world hypothesis, which suggests that RNA was the first molecule of life. According to this idea, RNA molecules form spontaneously in the primordial soup, eventually giving rise to self-replicating systems. Over time, these systems became more complex, leading to the first cells. While the RNA world hypothesis is compelling, it's not without challenges. How did RNA molecules form in the first place? And how did they transition to the DNA protein world we see today? These questions remain open, but they offer a fascinating glimpse into life's possible beginnings. Another theory takes us to the bottom of the ocean, where hydrothermal vents spew superheated water and minerals into the cold, dark depths. These vents are rich in chemicals and energy, creating an environment that some scientists believe could have sparked life. In the 1970s, the discovery of hydrothermal vents revolutionized our understanding of life's origins. These underwater chimneys host thriving ecosystems, powered not by sunlight but by chemical energy. This discovery showed that life doesn't need sunlight to survive, a crucial insight for understanding early Earth. Hydrothermal vents also provide the right conditions for the formation of organic molecules. The heat, minerals, and chemical gradients could have driven the reactions needed to create life's building blocks. Some scientists even suggest that the first cells formed in the porous rocks around these vents, protected from the harsh environment outside. This theory paints a vivid picture of life's beginnings, not in a tranquil soup, but in the fiery, dynamic depths of the ocean. Could life have come from beyond Earth? This is the idea behind panspermia, the theory that life exists throughout the universe and is spread by comets, asteroids, and cosmic dust. Panspermia doesn't solve the problem of how life began. It just shifts it elsewhere. But it raises intriguing possibilities. For example, organic molecules have been found on meteorites, suggesting that the ingredients for life are common in the cosmos. Some scientists even propose that life could survive the journey through space, protected by the icy interiors of comets. If true, life on Earth might have extraterrestrial origins, making us all, in a sense, children of the stars. While panspermia is still speculative, it reminds us that the story of life might be a cosmic one, spanning galaxies and eons. Was life's origin a fluke, or was it inevitable? This question lies at the heart of the origins debate. Some scientists, like Jacques Monod, argue that life was a chance event, a lucky combination of molecules in the right place at the right time. If this is true, life might be rare in the universe, a fleeting spark in the cosmic darkness. Others, like Stuart Kauffman, suggest that life is an emergent property of complex chemistry, a natural outcome of the laws of physics and chemistry. If this is true, Life might be common, arising wherever the conditions are right. This debate touches on deep philosophical questions about the nature of existence. Are we the result of random chance, or are we part of a grand, inevitable process? The answer, like the origins of life itself, remains elusive. To unravel the mystery of life's origins, scientists are conducting experiments and exploring extreme environments on Earth and beyond. In labs around the world, researchers are recreating the conditions of early Earth, testing how organic molecules form and interact. They're studying the chemistry of hydrothermal vents, the behavior of RNA, and the potential for life on other planets. Space missions are also playing a key role. Probes to Mars, Europa, and Enceladus are searching for signs of past or present life, while telescopes scan distant exoplanets for biosignatures. Each discovery brings us closer to understanding how life began and whether it exists elsewhere. Yet, despite our advances, the origins of life remain a mystery. It's a reminder of how much we still have to learn and how vast and complex the universe truly is. As we ponder the origins of life, we're reminded of the miracle of existence. Life is fragile, fleeting, and infinitely precious. It's a spark in the darkness, a dance of molecules that has endured for billions of years. The mystery of life's beginnings invites us to wonder, to explore, and to marvel at the beauty of the cosmos. Whether life arose in a primordial soup, a hydrothermal vent, or a distant star system, its story is a testament to the power of chemistry, the resilience of matter, and the endless possibilities of the universe. Take a moment to reflect on the journey that brought us here. From the first molecules to the first cells, from the depths of the ocean to the vastness of space, the story of life is a story of connection, creativity, and wonder. It's a story that continues to unfold, with each of us playing a part in its endless tapestry. The fine-tuning problem. The universe is a place of astonishing precision. From the vast expanse of galaxies to the tiniest particles, everything seems to follow a delicate balance, a set of rules so finely tuned that even the slightest change would render existence impossible. This delicate balance is known as the fine-tuning problem, and it's one of the most profound mysteries in science. Imagine a universe where the force of gravity was just a little stronger. Stars would burn out too quickly, collapsing into black holes before life could emerge. Or picture a universe where the electromagnetic force was slightly weaker. Atoms wouldn't hold together, and molecules, the building blocks of life, could never form. These are not just hypothetical scenarios. They are glimpses into what might have been, had the constants of nature been even slightly different. The fine-tuning problem asks why the universe seems so perfectly calibrated for life. The fundamental constants, such as numbers like the strength of gravity, the mass of electrons, and the speed of light, appear to be set with incredible precision. If any of these values were even slightly different, the universe as we know it would not exist. Stars wouldn't shine, planets wouldn't form, and life would be impossible. This precision has led some to wonder, is the universe designed for life, or is there a deeper explanation? The question touches on the very nature of reality, challenging us to think beyond the limits of our understanding. One possible explanation is the anthropic principle, which suggests that the universe appears fine-tuned because we are here to observe it. In other words, if the constants of nature were not just right, we wouldn't exist to ask the question. This idea shifts the focus from why the universe is fine-tuned to why we find ourselves in a universe that allows our existence. But the anthropic principle doesn't fully resolve the mystery. It raises further questions. Are there other universes where the constants are different? And if so, why do we live in this one? This line of thinking leads us to the multiverse hypothesis, the idea that our universe is just one of countless others, each with its own set of physical laws. In a multiverse, every possible combination of constants exists somewhere. Most universes would be lifeless, with stars that never form or atoms that never bond. But in a rare few, the constants would align perfectly, allowing galaxies, planets, and life to emerge. If true, our universe isn't special, it's just one of the lucky ones. The multiverse hypothesis is both exhilarating and humbling. It suggests that the universe is far larger and stranger than we can imagine, with infinite possibilities waiting to be explored. Yet it also raises questions about the nature of reality. If every possible universe exists, what does that mean for our sense of purpose? Are we just a random outcome in an infinite sea of possibilities? Another perspective comes from string theory, which proposes that the fundamental constants are not arbitrary, but determined by the geometry of higher dimensions. In this view, the universe's fine-tuning might be a natural consequence of its underlying structure. String theory is still speculative, but it offers a potential explanation for why the constants of nature are what they are. Yet, even with these ideas, the fine-tuning problem remains unresolved. It challenges us to confront the limits of our knowledge and to wonder whether the universe is the result of chance, necessity, or something beyond our understanding. The problem also has philosophical implications. For some, the fine-tuning of the universe suggests the existence of a cosmic designer, a force or intelligence that set the constants with purpose. This idea resonates with religious and spiritual traditions, which see the universe as a creation imbued with meaning. Others argue that fine-tuning is a natural outcome of the laws of physics. Perhaps the constants are not arbitrary but emerge from deeper principles we have yet to discover. This view aligns with the scientific quest for a theory of everything, a framework that unites all the forces of nature into a single, elegant equation. The fine-tuning problem also invites us to reflect on our place in the cosmos. If the universe is fine-tuned for life, what does that mean for us? Are we the intended outcome of a grand design? Or are we simply the result of random chance? These questions touch on the very essence of existence, challenging us to think deeply about who we are and why we are here. One way to approach the problem is through the lens of probability. The odds of the constants of nature aligning perfectly for life seem astronomically low. Yet, here we are, in a universe that allows stars to shine, planets to form, and life to flourish. This apparent improbability has led some to suggest that the universe is not just fine-tuned, but fine-tuned for discovery. The idea is that the constants of nature are not only set to allow life, but also to allow intelligent beings to explore and understand the cosmos. For example, the strength of the nuclear forces allows stars to produce carbon, the element essential for life as we know it. At the same time, the transparency of the universe allows light to travel vast distances, enabling us to observe distant galaxies and unravel the mysteries of the cosmos. This perspective shifts the focus from why the universe is fine-tuned to why we are able to perceive and understand it. It suggests that the universe is not just a place for life, but a place for curiosity, exploration, and wonder. The fine-tuning problem also connects to the broader question of cosmic purpose. If the universe is fine-tuned for life, does that mean it has a purpose? Or is purpose something we create, a story we tell ourselves to make sense of our existence? These questions have no easy answers, but they invite us to think deeply about the nature of reality and our place within it. The fine-tuning problem is not just a scientific puzzle, it's a philosophical one, a reminder that the universe is far stranger and more beautiful than we can imagine. As we explore the mysteries of fine-tuning, we are reminded of the delicate balance that makes life possible. The constants of nature are not just numbers, they are the threads that weave the fabric of reality. They shape the stars, the planets, and the very atoms that make up our bodies. The fine-tuning problem is a testament to the power of curiosity, the drive to explore the unknown, and the wonder of existence itself. It challenges us to think beyond the limits of our understanding, to embrace the mystery, and to marvel at the infinite possibilities of the cosmos. Take a moment to reflect on the precision of the universe. From the vastness of galaxies to the intricacy of atoms, everything is connected by a delicate balance, a harmony that allows life to exist. Whether the universe is fine-tuned by chance, necessity, or design, its beauty and complexity are undeniable. The fine-tuning problem invites us to wonder, to explore, and to dream. It reminds us that the universe is not just a place of matter and energy, but a place of meaning and mystery. And in that mystery lies the beauty of existence, a beauty that continues to inspire and challenge us as we seek to understand our place in the grand tapestry of the cosmos. The mystery of quantum gravity. The universe is governed by two great theories: quantum mechanics, which describes the behavior of the smallest particles, and general relativity, which explains the force of gravity and the structure of spacetime. Each theory has been incredibly successful in its own domain. Quantum mechanics predicts the behavior of atoms and particles with astonishing precision, while general relativity has given us black holes, gravitational waves, and the expanding universe. Yet, despite their successes, these two theories are fundamentally incompatible. Quantum mechanics deals with probabilities and uncertainties, where particles can exist in multiple states at once. General relativity, on the other hand, describes gravity as the curvature of spacetime, a smooth and deterministic fabric. When we try to combine them, the equations break down, leading to infinities and paradoxes. This incompatibility lies at the heart of the mystery of quantum gravity, one of the greatest challenges in modern physics. It's a quest to find a unified theory that can describe the universe at all scales, from the tiniest particles to the vastness of spacetime. The need for quantum gravity becomes most apparent in extreme environments, like the center of a black hole or the first moments of the Big Bang. In these regions, gravity becomes incredibly strong, and quantum effects cannot be ignored. Without a theory of quantum gravity, we cannot fully understand these cosmic phenomena or answer fundamental questions about the nature of reality. One of the most promising candidates for quantum gravity is string theory. This theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings can vibrate at different frequencies, giving rise to the various particles and forces we observe. String theory is elegant and mathematically beautiful, but it's also incredibly complex. It requires extra dimensions of space, up to 10 or 11 in some versions, that are curled up so small we can't detect them. These extra dimensions might hold the key to unifying gravity with the other forces of nature, but they also make string theory difficult to test experimentally. Despite its challenges, string theory has inspired new ways of thinking about the universe. It suggests that spacetime might not be fundamental, but emerge from deeper, more abstract principles. This idea has led to fascinating concepts like holography, where the information in a volume of space can be encoded on its boundary, like a hologram. Another approach to quantum gravity is loop quantum gravity. Unlike string theory, which tries to unify all forces, loop quantum gravity focuses specifically on quantizing spacetime itself. In this theory, spacetime is not smooth and continuous, but made of tiny discrete loops. These loops form a network, creating a kind of quantum foam at the smallest scales. Loop quantum gravity offers a radical new perspective on the nature of spacetime. It suggests that space and time are not fundamental, but emerge from the interactions of these loops. This idea has profound implications for our understanding of the universe, from the Big Bang to the nature of black holes. One of the most exciting predictions of loop quantum gravity is that the Big Bang might not have been the beginning of the universe, but a transition from a previous state. This idea, known as the Big Bounce, suggests that the universe undergoes endless cycles of expansion and contraction, each one giving rise to a new cosmos. Yet, like string theory, loop quantum gravity faces significant challenges. It's difficult to connect the theory to the world we observe, and experimental evidence remains elusive. Both theories are works in progress, each offering a glimpse into the possible nature of quantum gravity, but leaving many questions unanswered. The mystery of quantum gravity also touches on some of the deepest questions in physics. For example, what happens at the center of a black hole? According to general relativity, the center is a singularity, a point of infinite density where the laws of physics break down. But quantum mechanics suggests that infinities are impossible, hinting that our understanding is incomplete. Some theories propose that quantum gravity might resolve the singularity, replacing it with something else entirely. For example, in loop quantum gravity, the singularity might be replaced by a quantum bridge, connecting our universe to another. This idea is still speculative, but it offers a tantalizing possibility that black holes might be gateways to other realms. Another profound question is the nature of time. In general relativity, time is a dimension, part of the fabric of spacetime. But in quantum mechanics, time is treated differently, as a parameter that flows independently of space. Reconciling these two views is one of the central challenges of quantum gravity. Some theories suggest that time might not be fundamental but emerge from more basic principles. For example, in causal set theory, space-time is made of discrete events, connected by cause and effect. Time, in this view, is not a continuous flow, but a sequence of moments, like frames in a film. The mystery of quantum gravity also has philosophical implications. It challenges our understanding of reality, forcing us to rethink concepts like space, time, and matter. Are these things fundamental, or do they emerge from deeper, more abstract principles? This question touches on the very nature of existence. If space-time is not fundamental, what is? Is the universe made of information, relationships, or something else entirely? These ideas blur the line between physics and philosophy, inviting us to think deeply about the nature of reality. The quest for quantum gravity is not just a scientific endeavor, it's a journey of curiosity and wonder. It reminds us that the universe is far stranger and more complex than we can imagine, full of mysteries waiting to be unraveled. As we explore these mysteries, we are reminded of the power of human imagination and creativity. The theories of quantum gravity, string theory, loop quantum gravity, and others are not just mathematical models. They are stories we tell ourselves to make sense of the cosmos. These stories are still being written, and the final chapter is far from complete. But each step brings us closer to understanding the universe and our place within it. The mystery of quantum gravity is a testament to the power of curiosity, the drive to explore the unknown, and the wonder of existence itself. Take a moment to reflect on the beauty and complexity of the cosmos. From the tiniest particles to the vastness of space-time, everything is connected by the laws of physics. Yet, these laws are not fixed. They are evolving as we uncover new truths and challenge old assumptions. The mystery of quantum gravity invites us to wonder, to explore, and to dream. It reminds us that the universe is not just a place of matter and energy, but a place of meaning and mystery. And in that mystery lies the beauty of existence, a beauty that continues to inspire and challenge us as we seek to understand our place in the grand tapestry of the cosmos. The search for extraterrestrial intelligence. The universe is vast, almost unimaginably so, with hundreds of billions of galaxies, each containing hundreds of billions of stars. The sheer scale of the cosmos is humbling. Among these countless stars, there are trillions of planets, many of which lie in the habitable zone, the region where conditions might be right for liquid water, and perhaps for life. Given these numbers, it seems almost inevitable that life exists elsewhere. And if life exists, could intelligence also arise? This question lies at the heart of the search for extraterrestrial intelligence, or SETI. The search for extraterrestrial intelligence is not just a scientific endeavor. It's a profound exploration of our place in the universe. It challenges us to think beyond the boundaries of our planet, to imagine civilizations that might be vastly older, wiser, or stranger than our own. It's a quest that combines curiosity, hope, and a deep sense of wonder. The modern search for extraterrestrial intelligence began in earnest in the 20th century, fueled by advances in astronomy and technology. In 1959, physicists Giuseppe Cocconi and Philip Morrison published a groundbreaking paper suggesting that extraterrestrial civilizations might use radio waves to communicate across the stars. Radio waves, they argued, are an efficient way to transmit information over vast distances, and they can travel through the vacuum of space without being absorbed or scattered. This idea inspired astronomer Frank Drake to conduct the first organized SETI experiment in 1960. Using a radio telescope in West Virginia, Drake scanned two nearby stars, Tau Ceti and Epsilon Eridani, for signs of artificial signals. Although he found nothing, his experiment marked the beginning of a new era in the search for extraterrestrial intelligence. Since then, SETI has grown into a global effort, with scientists using increasingly sophisticated tools to scan the skies for signals. Radio telescopes, like the Arecibo Observatory in Puerto Rico and the Allen Telescope Array in California, have listened for patterns that might indicate intelligent origin, narrowband signals, repeating pulses, or mathematical sequences. But the search is not limited to radio waves. In recent years, scientists have expanded their efforts to include optical SETI, which looks for laser pulses, or other forms of light-based communication. They've also explored the possibility of detecting technosignatures, signs of advanced technology, such as megastructures orbiting distant stars or industrial pollution in exoplanet atmospheres. Despite decades of searching, we have yet to find definitive evidence of extraterrestrial intelligence. This absence of contact is known as the Great Silence, and it has led to a range of theories about why we might be alone or why we might not have found anyone yet. One possibility is that intelligent life is rare. The emergence of life itself might be a fluke, requiring a precise combination of conditions that are unlikely to occur elsewhere. Even if life does arise, the leap to intelligence might be even rarer. Earth's history is filled with chance events, asteroid impacts, climate shifts, and evolutionary breakthroughs that shape the course of life. If any of these events had gone differently, intelligence might never have emerged. Another possibility is that intelligent civilizations are short-lived. Technological advancement might come with risks such as nuclear war, environmental collapse, or the misuse of artificial intelligence. If civilizations tend to self-destruct, the window for communication might be narrow, making it unlikely that we would detect them. Yet another idea is that we're simply not looking in the right way. Extraterrestrial civilizations might use forms of communication we haven't yet imagined, or they might be so advanced that their technology is beyond our comprehension. They might even be deliberately avoiding contact, observing us from a distance like scientists studying a fragile ecosystem. The search for extraterrestrial intelligence is not just about finding others, it's also about understanding ourselves. The possibility of contact raises profound questions about what it means to be human, about our values, our fears, and our place in the cosmos. What would it mean to discover that we are not alone? How would it change our view of ourselves and our planet? Some believe that contact with an advanced civilization could bring immense benefits, from technological breakthroughs to new philosophical insights. Others worry that it could be destabilizing, challenging our beliefs and institutions in ways we can't predict. The search for extraterrestrial intelligence also invites us to reflect on our own behavior. If we are sending signals into space, what message are we conveying? Are we representing the best of humanity, or are we revealing our flaws and conflicts? These questions remind us that the search for extraterrestrial intelligence is not just a scientific endeavor, it's a moral and ethical one as well. In recent years, the search for extraterrestrial intelligence has expanded beyond traditional SETI efforts. Breakthrough Listen, a $100 million initiative funded by billionaire Yuri Milner, is one of the most ambitious projects to date. Using some of the world's most powerful telescopes, Breakthrough Listen is scanning millions of stars for signs of intelligent life, with a focus on nearby star systems and the center of the Milky Way. At the same time, the discovery of thousands of exoplanets has given new hope to the search. Planets like Proxima Centauri b, which orbits the closest star to our Sun, and the 7 Earth-sized planets in the TRAPPIST-1 system, have sparked excitement about the possibility of finding habitable worlds. While these planets are too far away for us to visit, they are prime targets for the search for biosignatures, chemical signs of life, and technosignatures. The search for extraterrestrial intelligence is also intertwined with the broader search for life in the universe. Missions to Mars, Europa, and Enceladus are exploring the possibility of microbial life within our own solar system. While these efforts focus on simpler forms of life, they are part of the same quest to understand whether life is a rare fluke or a common feature of the cosmos. As we continue to search, we are reminded of the vastness and mystery of the universe. The stars we see in the night sky are just a tiny fraction of what's out there, and each one could be the home of a civilization we have yet to discover. The search for extraterrestrial intelligence is a journey of curiosity, hope, and wonder, a testament to our desire to connect with the cosmos and to understand our place within it. Take a moment to imagine the possibilities. Out there, Among the stars, there might be civilizations far older and wiser than our own. They might have faced challenges we can't yet imagine, and they might have answers to questions we haven't even asked. They might be looking for us, just as we are looking for them. The search for extraterrestrial intelligence is not just about finding others, it's about finding ourselves. It's a reminder that we are part of something much larger, a universe filled with wonder and mystery. Whether or not we ever make contact, the search itself is a testament to the power of curiosity, the drive to explore the unknown, and the wonder of existence. As you reflect on the vastness of the cosmos, let your mind wander through the possibilities. Imagine the civilizations that might be out there, the stories they might tell, and the wisdom they might share. The search for extraterrestrial intelligence is a journey of discovery, a journey that continues to inspire and challenge us as we seek to understand our place in the grand tapestry of the universe. The nature of time. In our previous exploration of the arrow of time, we delved into the mystery of why time flows in one direction, why we remember the past but not the future, and why certain processes, like the breaking of an egg, are irreversible. The arrow of time is about the directionality of time, shaped by the rise of entropy and the laws of thermodynamics. But now, let's turn our attention to a deeper question. What is time itself? This is the mystery of the nature of time, a journey into the essence of time, its fundamental properties, and its role in the fabric of reality. Time is one of the most familiar yet enigmatic aspects of our existence. It shapes our lives, marking the passage of moments, days, and years. We measure it, plan around it, and often feel like there's never enough of it. Yet, despite its familiarity, time remains one of the deepest mysteries in science and philosophy. Is time a fundamental dimension of the universe? Or is it an illusion created by our minds? Does it flow like a river? Or is it a static structure where past, present, and future coexist? These questions lie at the heart of our exploration. In physics, time is treated as a dimension, part of the fabric of spacetime. According to Einstein's theory of relativity, time is not absolute but relative, stretching and compressing depending on speed and gravity. A clock on a fast-moving spaceship ticks slower than one on Earth, a phenomenon known as time dilation. Similarly, time runs slower near a massive object like a black hole, where gravity is incredibly strong. These effects have been confirmed by experiments, such as those using atomic clocks on airplanes and satellites. They reveal that time is not a fixed backdrop but a dynamic, flexible dimension, intertwined with space in ways that challenge our everyday intuition. Yet, while relativity treats time as a dimension, it doesn't explain why time flows in one direction. This is where the arrow of time comes in, tied to the concept of entropy and the second law of thermodynamics. But the nature of time goes beyond directionality, asking what time is at its core. Is it a fundamental property of the universe, or does it emerge from more basic principles? One of the most intriguing ideas about the nature of time comes from quantum mechanics. At the quantum level, particles exist in a state of superposition, meaning they can be in multiple states at once. When we observe them, they collapse into a single state, but the equations of quantum mechanics are time-symmetric. They work equally well in reverse. This raises the question, is time fundamental, or is it an emergent property of quantum interactions? Some theories, like causal set theory, suggest that time is not continuous, but made of discrete moments, like frames in a film. In this view, time is not a smooth, flowing river, but a series of individual events, connected by cause and effect. This idea challenges our everyday understanding of time as a continuous flow and suggests that the passage of time might be an illusion created by the way our brains process information. Another radical idea is that time might not be fundamental at all. In loop quantum gravity, space-time itself is quantized, emerging from the interactions of tiny loops. These loops form a network, creating a kind of quantum foam at the smallest scales. Time, in this view, is not a separate dimension, but a property that emerges from the relationships between these loops. This idea has profound implications for our understanding of the universe. If time is not fundamental, what does that mean for our experience of it? Are we merely passengers on the river of time, carried along by forces beyond our control? Or are we active participants, shaping the flow of time through our choices and actions? The mystery of time also touches on some of the deepest questions in physics. For example, what happens to time at the center of a black hole? According to general relativity, time and space swap roles, turning the singularity into a moment in time rather than a point in space. This bizarre reversal challenges our understanding of time and suggests that it might not be as fundamental as we think. Similarly, the heat death of the universe, a state of maximum entropy where all activity ceases, raises questions about the ultimate fate of time. If entropy reaches its maximum, will time lose its meaning? Or will it continue to flow in some abstract sense, even in a universe where nothing happens? The nature of time also has philosophical implications. It challenges us to think about the nature of existence, about what it means to be present, and about the relationship between past, present, and future. In many ways, time is the thread that weaves the fabric of our lives. It gives us a sense of continuity, connecting our memories, our experiences, and our hopes for the future. Yet, it is also fleeting, slipping through our fingers no matter how tightly we try to hold on. The nature of time invites us to reflect on our place in the universe. Are we merely passengers on the river of time, carried along by forces beyond our control? Or are we active participants, shaping the flow of time through our choices and actions? As we ponder these questions, we are reminded of the beauty and mystery of existence. Time is not just a physical quantity, it is a source of wonder, a reminder of the fleeting nature of life and the infinite possibilities of the cosmos. Take a moment to reflect on the nature of time. Feel the rhythm of your breath, the beat of your heart, the flow of your thoughts. In this moment, you are connected to the vast tapestry of time, a thread in the infinite fabric of the universe. The mystery of time is not just a scientific puzzle. It is a journey of curiosity, wonder, and reflection. It challenges us to think beyond the limits of our understanding, to embrace the unknown, and to marvel at the infinite possibilities of existence. As you drift into relaxation, let your mind wander through the mysteries of time. Imagine the moments that have shaped your life, the memories that define you, and the future that lies ahead. Time is not just a dimension. It is a story, a journey, and a testament to the beauty of existence. The mystery of time is not just a scientific puzzle. It is a journey of curiosity, wonder, and reflection. It challenges us to think beyond the limits of our understanding, to embrace the unknown, and to marvel at the infinite possibilities of existence. As you drift into relaxation, let your mind wander through the mysteries of time. Imagine the moments that have shaped your life, the memories that define you, and the future that lies ahead. Time is not just a dimension. It is a story, a journey, and a testament to the beauty of existence. What they found was astonishing. Galaxy clusters were moving in a way that couldn't be explained by the known forces of the universe. They weren't just being carried along by the expansion of space. They were being pulled in a specific direction, as if by an unseen force. This motion, dubbed dark flow, suggested that something beyond the observable universe was exerting a gravitational influence. The discovery of dark flow was met with both excitement and skepticism. Could there really be structures or forces outside our universe, tugging on galaxy clusters like cosmic puppeteers? Or was there a simpler explanation, perhaps an error in the data, or an overlooked aspect of physics? To understand dark flow, we need to step back and consider the larger picture. The universe we can observe, the part illuminated by light and other forms of radiation, is vast, but it's not infinite. Beyond the observable universe lies the cosmic horizon, a boundary created by the finite speed of light and the age of the universe. We can't see beyond this horizon, but that doesn't mean nothing exists there. Dark flow suggests that there might be something beyond the cosmic horizon, something massive enough to pull on galaxy clusters across billions of light years. This idea is both thrilling and unsettling. It challenges the assumption that the universe is homogeneous and isotropic, the same in all directions, on the largest scales. One possibility is that dark flow is caused by a supervoid, a vast region of space with lower density than its surroundings. Supervoids can create gravitational effects, pulling matter toward them. However, the scale of dark flow is so large that it would require a supervoid far beyond the observable universe, raising questions about how such a structure could form. Another possibility is that dark flow is evidence of a multiverse, a collection of universes beyond our own. In this view, our universe might be one bubble in a frothy sea of universes, each with its own physical laws and properties. The gravitational pull of a neighboring universe could explain the mysterious motion of galaxy clusters. This idea is speculative, but it aligns with theories like cosmic inflation, which suggests that the early universe underwent a rapid expansion, creating regions that evolved into separate universes. If true, dark flow might be our first glimpse of a multiverse, a tantalizing hint of realities beyond our own. Yet, not all scientists are convinced. Some argue that dark flow could be an artifact of the data, a result of systematic errors or incomplete observations. Others suggest that it might be explained by new physics, such as modifications to Einstein's theory of general relativity, or the influence of dark energy, the mysterious force driving the accelerated expansion of the universe. The mystery of dark flow also raises deeper questions about the nature of the cosmos. If there are structures or forces beyond the observable universe, what does that mean for our understanding of reality? Are we just a small part of a much larger, more complex system? These questions touch on the limits of human knowledge. The cosmic horizon is a reminder that there are parts of the universe we can never see, regions forever hidden from our view. Yet dark flow suggests that these hidden regions might still influence us, pulling on the fabric of space-time in ways we can detect but not fully understand. The search for answers continues. Astronomers are using increasingly sophisticated tools to study dark flow, from space-based observatories like the Planck satellite to ground-based telescopes that map the distribution of galaxy clusters. Each new observation brings us closer to understanding this enigmatic phenomenon, but the mystery remains. Dark flow also invites us to reflect on our place in the cosmos. If there are forces or structures beyond the observable universe, what does that mean for our sense of scale and significance? Are we just a tiny speck in an infinite sea of universes? Or is there something special about our corner of reality? These questions are not just scientific, they are philosophical. They challenge us to think beyond the limits of our experience, to imagine realities that might be stranger and more beautiful than we can comprehend. The mystery of dark flow is a reminder that the universe is full of surprises. Just when we think we understand it, it reveals new layers of complexity, new puzzles to solve. This is the essence of science, a journey of curiosity, wonder, and discovery. As we explore the mystery of dark flow, we are reminded of the vastness and mystery of the cosmos. The universe is not just a collection of stars and galaxies. It is a dynamic, evolving system, full of forces and phenomena we have yet to understand. Take a moment to reflect on the mystery of dark flow. Imagine the galaxy clusters, pulled by an unseen force, moving through the vast expanse of space. What could be out there, beyond the cosmic horizon? What secrets does the universe hold, waiting to be discovered? The search for answers is not just about solving a scientific puzzle. It's about expanding our understanding of reality. It's about embracing the unknown, marveling at the beauty of the cosmos, and finding our place within it. As you drift into relaxation, let your mind wander through the mysteries of dark flow. Imagine the forces at work, the structures beyond our view, and the infinite possibilities of the universe. The mystery of dark flow is a testament to the power of curiosity, the drive to explore the unknown, and the wonder of existence itself. The puzzle of quantum entanglement. Imagine two particles, separated by vast distances, perhaps even light years apart. Despite the distance, they are intimately connected, their fates intertwined in a way that defies our everyday understanding of reality. If you measure one particle, the other instantly responds, as if they share a secret language that transcends space and time. This strange phenomenon is known as quantum entanglement, and it is one of the most baffling and beautiful mysteries in science. Quantum entanglement was first proposed in the 1930s by Albert Einstein, Boris Podolsky, and Nathan Rosen, who used it to argue that quantum mechanics was incomplete. Einstein famously called it spooky action at a distance, a phrase that captures both its mystery and its defiance of classical physics. Yet, decades of experiments have confirmed that entanglement is real, forcing us to rethink our understanding of the universe. At its core, quantum entanglement is a connection between particles that persists no matter how far apart they are. When two particles become entangled, their properties such as spin, polarization, or momentum are linked. Measuring one particle instantly determines the state of the other, even if they are on opposite sides of the galaxy. This connection seems to happen faster than the speed of light, challenging one of the cornerstones of Einstein's theory of relativity. How can this be? How can particles communicate instantaneously across vast distances? The answer lies in the strange and counterintuitive world of quantum mechanics, where particles exist in a state of superposition, meaning they can be in multiple states at once until they are observed. Entanglement takes this idea further, linking the states of two or more particles in a way that defies classical logic. One of the most famous experiments demonstrating entanglement is the Bell test, named after physicist John Bell. In the 1960s, Bell proposed a way to test whether entanglement could be explained by hidden variables, unknown properties that determine the particle's behavior in advance. If hidden variables existed, the results of measurements on entangled particles would fall within certain limits. But if quantum mechanics was correct, the results would violate these limits, proving that entanglement was truly non-local. In the decades since, numerous experiments have confirmed that entanglement violates Bell's limits, ruling out the possibility of hidden variables. These experiments have been conducted with photons, electrons, and even entire atoms, all showing the same eerie connection between entangled particles. The results are clear. Entanglement is a fundamental feature of the quantum world, and it cannot be explained by any classical theory. But what does this mean for our understanding of reality? If entangled particles can influence each other instantaneously, does this imply that space and time are not as fundamental as we thought? Some physicists, like David Bohm, have proposed that entanglement points to a deeper, hidden order in the universe, where everything is interconnected in ways we cannot yet see. Others, like Hugh Everett, suggest that entanglement is evidence of the many worlds interpretation of quantum mechanics. In this view, every possible outcome of a quantum measurement actually happens, but in separate, parallel universes. When two particles become entangled, their states are linked across these universes, creating a web of connections that spans the multiverse. Yet another perspective comes from quantum field theory, which describes particles as excitations of underlying fields. In this framework, entanglement might arise from the deep connections between these fields, which permeate all of space and time. This idea blurs the line between particles and the space they inhabit, suggesting that entanglement is not just a property of particles, but of the fabric of reality itself. The implications of entanglement extend far beyond the realm of physics. They challenge our understanding of causality, the idea that cause must precede effect. If entangled particles can influence each other instantaneously, does this mean that cause and effect can operate outside the bounds of time? Some experiments have even suggested that entanglement might allow for a form of retrocausality, where future events can influence the past. Entanglement also has practical applications, particularly in the field of quantum computing. By harnessing the power of entangled particles, quantum computers can perform calculations that would be impossible for classical computers. This could revolutionize fields like cryptography, materials science, and artificial intelligence, opening up new possibilities for solving some of humanity's greatest challenges. But perhaps the most profound implication of entanglement is what it tells us about the nature of reality. In a universe where particles can be instantaneously connected across vast distances, the idea of separateness begins to break down. We are not isolated beings in a cold, indifferent cosmos. We are part of a vast, interconnected web, where every particle, every atom, every star is linked in ways we are only beginning to understand. This interconnectedness invites us to reflect on our place in the universe. If particles can be entangled across space and time, what does that mean for us? Are we too connected in ways we cannot see? Could entanglement be a glimpse of a deeper unity, a hidden harmony that underlies all of existence? The mystery of quantum entanglement is not just a scientific puzzle, it is a journey into the heart of reality itself. It challenges us to think beyond the limits of our intuition, to embrace the strange and beautiful truths of the quantum world. It reminds us that the universe is far more mysterious and wondrous than we can imagine, full of connections and possibilities that defy explanation. Take a moment to imagine the entangled particles, their states linked across the vastness of space. Picture the web of connections that binds them, a tapestry of light and energy that stretches across the cosmos. In this moment, you are part of that tapestry, connected to the universe in ways that are both profound and mysterious. The puzzle of quantum entanglement is a reminder that the universe is not just a collection of isolated objects, but a dynamic, interconnected whole. It invites us to explore the deeper truths of reality, to marvel at the beauty of the quantum world, and to wonder what other mysteries lie waiting to be discovered. Let your thoughts linger on the entangled particles, their connection a symbol of the unity that underlies all of existence. In their strange and beautiful dance, we find a reflection of our own place in the cosmos, a reminder that we are all part of something greater, something infinite, something eternal. The enigma of black hole singularities. At the heart of every black hole lies a mystery so profound that it challenges our understanding of reality itself. This mystery is the singularity, a point of infinite density where the laws of physics as we know them break down. It is a place where space and time cease to exist, where matter is crushed into an infinitely small point, and where the very fabric of reality is stretched beyond comprehension. The singularity is the ultimate enigma, a cosmic riddle that has puzzled scientists for decades. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse under their own weight, creating a gravitational pull so intense that it warps the fabric of space-time. The boundary of a black hole, known as the event horizon, marks the point of no return. Once something crosses this boundary, it is inexorably drawn toward the singularity at the center. But what lies within the event horizon? What happens to matter and energy as they approach the singularity? These questions take us to the edge of our understanding, where the familiar rules of physics no longer apply. According to Einstein's theory of general relativity, the singularity is a point of infinite density and zero volume. It is a place where the curvature of space-time becomes infinite, and the gravitational field becomes infinitely strong. At the singularity, the equations of general relativity break down, and our ability to predict what happens next comes to an end. This breakdown is not just a mathematical curiosity. It is a fundamental challenge to our understanding of the universe. Infinite densities and zero volumes are not physical realities, but signs that our theories are incomplete. They suggest that there is something deeper, something beyond general relativity, that we have yet to discover. One of the most promising candidates for resolving the singularity is quantum gravity, a theory that seeks to unify general relativity with quantum mechanics. Quantum mechanics describes the behavior of particles at the smallest scales, where the rules of classical physics no longer apply. It is a world of probabilities, uncertainties, and strange phenomena like superposition and entanglement. At the singularity, the effects of quantum mechanics become crucial. The extreme conditions, infinite density, infinite curvature, require a quantum description of gravity, something that general relativity cannot provide. But despite decades of effort, a complete theory of quantum gravity remains elusive. One approach to quantum gravity is string theory, which proposes that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. These strings exist in a higher dimensional space, and their vibrations give rise to the particles and forces we observe. In string theory, the singularity might be replaced by a quantum bridge, a region where the fabric of space-time is smoothed out by quantum effects. Another approach is loop quantum gravity, which suggests that space-time itself is made of discrete loops. These loops form a network, creating a kind of quantum foam at the smallest scales. In this view, The singularity might be replaced by a quantum bounce, where the collapsing matter rebounds and creates a new universe. These ideas are still speculative, but they offer a glimpse of what might lie beyond the singularity. They suggest that the singularity is not the end of the story, but a gateway to new realms of physics, new dimensions of reality, and new possibilities for the universe. The mystery of the singularity also raises profound questions about the nature of space and time. In general relativity, space and time are part of a single four-dimensional fabric called space-time. But at the singularity, this fabric is torn apart, and the distinction between space and time becomes meaningless. Some theories suggest that space and time might emerge from more fundamental principles, like quantum entanglement or the interactions of particles. In this view, the singularity is not a point of infinite density, but a place where the underlying structure of reality is revealed. The singularity also challenges our understanding of causality, the idea that cause must precede effect. Near the singularity, the extreme curvature of spacetime can create closed time-like curves, paths that loop back on themselves and allow for time travel. This raises the possibility of paradoxes, like the famous grandfather paradox, where traveling back in time could prevent your own existence. These paradoxes are not just theoretical curiosities. They are signs that our understanding of time is incomplete. They suggest that time might not be a fundamental property of the universe, but an emergent phenomenon, something that arises from deeper, more abstract principles. The singularity also has implications for the ultimate fate of the universe. If black holes can form singularities, could the entire universe collapse into one? This idea, known as the Big Crunch, suggests that the universe might end in a singularity, just as it began in the Big Bang. But the singularity is not just a scientific puzzle. It is also a philosophical one. It challenges us to think about the nature of existence, about what it means to be real, and about the limits of human knowledge. In many ways, the singularity is a mirror, reflecting our deepest questions and fears. It is a place where the known meets the unknown, where the finite meets the infinite, and where the possible meets the impossible. It is a reminder that the universe is far stranger and more beautiful than we can imagine, full of mysteries that defy explanation. Let your thoughts linger on the singularity, a point of infinite density and infinite mystery. Picture the fabric of spacetime, stretched and twisted by the immense gravity of the black hole. Imagine the particles and energy, drawn inexorably toward the center, where the laws of physics break down and new possibilities emerge. The singularity is not just a scientific challenge. It is a journey into the heart of reality. It invites us to explore the deepest truths of the universe, to marvel at the beauty of the cosmos, and to wonder what lies beyond the edge of our understanding. Take a moment to reflect on the singularity, a place where space and time cease to exist, where matter is crushed into an infinitely small point, and where the very fabric of reality is stretched beyond comprehension. In this moment, you are connected to the vast tapestry of the universe, a thread in the infinite fabric of existence. The enigma of the singularity is a reminder that the universe is not just a collection of isolated objects, but a dynamic, interconnected whole. It challenges us to think beyond the limits of our intuition, to embrace the strange and beautiful truths of the cosmos, and to wonder what other mysteries lie waiting to be discovered. Let your imagination wander through the mysteries of the singularity, a place where the known meets the unknown, where the finite meets the infinite, and where the possible meets the impossible. In its strange and beautiful dance, we find a reflection of our own place in the cosmos, a reminder that we are all part of something greater, something infinite, something eternal. The mystery of the great attractor. Imagine the universe as a vast interconnected web, with galaxies and galaxy clusters strung like beads on invisible threads. These threads are the gravitational forces that bind the cosmos together, shaping its structure and guiding its motion. But in this cosmic web, there is a mystery, a gravitational anomaly so powerful that it is pulling thousands of galaxies, including our own Milky Way, toward it at incredible speeds. This mystery is known as the Great Attractor, and it is one of the most intriguing puzzles in modern cosmology. The story of the Great Attractor begins in the 1970s, when astronomers noticed something unusual about the motion of galaxies in our local universe. While the expansion of the universe causes most galaxies to move away from us, some galaxies were moving in a particular direction, as if being pulled by an unseen force. This motion was not random. It was a coordinated flow, suggesting the presence of a massive gravitational source. Further observations revealed that the Milky Way, along with thousands of other galaxies, is being drawn toward a region of space located about 250 million light-years away, in the direction of the constellations Centaurus and Hydra. This region became known as the Great Attractor, a gravitational focal point that defies easy explanation. But what exactly is the Great Attractor? What could be massive enough to exert such a powerful gravitational pull on so many galaxies? The answer lies in the distribution of matter in the universe, a cosmic tapestry woven by gravity over billions of years. One possibility is that the Great Attractor is a massive cluster of galaxies, a dense region of space where thousands of galaxies are packed together. Galaxy clusters are among the largest structures in the universe, and their immense gravitational pull can influence the motion of galaxies over vast distances. However, observations of the Great Attractor region have revealed that it is not as dense as expected. While there are galaxy clusters in the area, they do not seem to account for the full strength of the gravitational pull. This discrepancy has led scientists to propose that the Great Attractor might be part of an even larger structure, a supercluster of galaxies that extends far beyond what we can currently observe. Superclusters are the largest known structures in the universe, spanning hundreds of millions of light-years and containing thousands of galaxy clusters. The Great Attractor could be the gravitational center of such a supercluster, its pull amplified by the combined mass of countless galaxies. But the mystery deepens when we consider what lies beyond the Great Attractor. In the 1980s, astronomers discovered that the Great Attractor itself is being pulled toward an even more massive structure, known as the Shapley Attractor. Located about 650 million light-years away, the Shapley Attractor is the largest concentration of matter in the observable universe, a colossal supercluster that exerts a gravitational influence on everything around it. This discovery suggests that the Great Attractor is not an isolated anomaly but part of a vast cosmic flow, a river of galaxies moving through the universe under the influence of gravity. The Milky Way, along with thousands of other galaxies, is caught in this flow, carried along by the gravitational currents that shape the cosmos. Yet despite these insights, the Great Attractor remains shrouded in mystery. One of the challenges in studying it is its location in the zone of avoidance, a region of the sky obscured by the dense dust and stars of the Milky Way's galactic plane. This makes it difficult to observe the Great Attractor directly, forcing astronomers to rely on indirect methods, such as mapping the motion of galaxies and studying the cosmic microwave background radiation. Recent advances in technology, such as infrared and radio telescopes, have begun to pierce the veil of the zone of avoidance, revealing more about the Great Attractor and its surroundings. These observations have uncovered new galaxy clusters and superclusters, adding pieces to the puzzle but also raising new questions. The mystery of the Great Attractor also has profound implications for our understanding of the universe. It challenges the assumption that the universe is homogeneous and isotropic, the same in all directions, on the largest scales. Instead, it suggests that the distribution of matter is uneven, with vast regions of emptiness punctuated by dense concentrations of galaxies. This uneven distribution is a reminder that the universe is a dynamic, evolving system, shaped by the interplay of gravity, dark matter, and dark energy. The Great Attractor is a testament to the power of gravity, a force that binds the cosmos together and guides its motion on the grandest scales. But the Great Attractor is more than just a scientific puzzle. It is also a philosophical one. It invites us to think about our place in the universe, about the forces that shape our existence, and about the mysteries that lie beyond our understanding. Let your thoughts linger on the Great Attractor, a gravitational enigma that pulls thousands of galaxies toward it. Picture the Milky Way, caught in its flow, moving through the vast expanse of space toward an unseen destination. Imagine the countless galaxies, each with its own stars, planets, and possibilities, all drawn together by the invisible hand of gravity. The Great Attractor is a reminder that the universe is not just a collection of isolated objects, but a dynamic, interconnected whole. It challenges us to think beyond the limits of our intuition, to embrace the strange and beautiful truths of the cosmos, and to wonder what other mysteries lie waiting to be discovered. Take a moment to reflect on the Great Attractor, a gravitational focal point that defies easy explanation. In its pull, we find a symbol of the unity that underlies all of existence, a reminder that we are all part of something greater, something infinite, something eternal. The mystery of the Great Attractor is not just a scientific challenge. It is a journey into the heart of reality. It invites us to explore the deepest truths of the universe, to marvel at the beauty of the cosmos, and to wonder what lies beyond the edge of our understanding. Let your imagination wander through the mysteries of the Great Attractor, a place where the known meets the unknown, where the finite meets the infinite, and where the possible meets the impossible. In its strange and beautiful dance, we find a reflection of our own place in the cosmos, a reminder that we are all part of something greater, something infinite, something eternal. The mystery of the moon's magnetic field. The moon, Earth's closest celestial companion, has long been a source of wonder and mystery. Its silvery light has inspired poets, scientists, and dreamers for millennia. Yet, despite its familiarity, the moon holds secrets that challenge our understanding of planetary science. One of the most intriguing of these secrets is the mystery of its magnetic field. Today, the moon has no global magnetic field, the kind that surrounds Earth and protects it from harmful solar radiation. But billions of years ago, the moon's story was very different. Rocks brought back by the Apollo missions reveal that the moon once had a magnetic field, one that was surprisingly strong, comparable to Earth's at times. This discovery has puzzled scientists for decades. How could the moon, a much smaller and less dynamic body than Earth, have generated such a powerful magnetic field? And why did it disappear? To understand this mystery, we must first explore how magnetic fields are generated. On Earth, the magnetic field is created by the dynamo effect, a process driven by the movement of molten iron in the planet's outer core. As the liquid metal swirls and churns, it generates electric currents, which in turn produce a magnetic field. This self-sustaining process requires three key ingredients: a molten core, convection, the movement of heat, and rotation. The moon, however, is much smaller than Earth, with a core that is proportionally tiny. Its interior cooled rapidly after its formation, and today, its core is thought to be mostly solid. This raises a fundamental question. How could the moon have generated a magnetic field without the conditions necessary for a dynamo? One possibility is that the moon's magnetic field was powered by a different mechanism, one unique to its early history. During its formation, the moon is thought to have been much closer to Earth, and the gravitational interactions between the two bodies may have generated intense tidal forces. These forces could have stirred the moon's interior, creating the motion needed to drive a dynamo. Another theory suggests that the moon's magnetic field was generated by impact-driven dynamos. In its early history, the moon was bombarded by massive asteroids and comets, collisions so powerful that they could have melted parts of the moon's interior. This melting could have created temporary pockets of molten metal, generating short-lived magnetic fields. Over time, as the impacts became less frequent and the moon's interior cooled, the magnetic field would have faded away. Yet another idea is that the moon's magnetic field was powered by precession, a wobbling motion caused by the gravitational pull of Earth. This wobbling could have stirred the moon's core, creating the conditions needed for a dynamo. However, this theory requires the moon's core to have remained molten for much longer than current models suggest, raising new questions about the moon's thermal history. The mystery of the moon's magnetic field is not just a scientific puzzle. It is a window into the moon's past and the dynamic processes that shaped it. By studying the magnetic properties of lunar rocks, scientists can piece together the story of the moon's early history, a time when it was a much more active and volatile place. But the moon's magnetic field is not just a relic of the past, it also has implications for the future. Understanding how the moon generated and lost its magnetic field could shed light on the evolution of other rocky bodies, including planets and moons in distant star systems. It could also help us better understand the processes that drive planetary magnetic fields, including Earth's, and how they protect life from harmful solar radiation. The mystery of the moon's magnetic field also invites us to reflect on the nature of time and change. The moon, once a dynamic and active world, is now a quiet and desolate place. Its magnetic field, once strong enough to rival Earth's, has faded into nothingness. This transformation is a reminder that the universe is constantly evolving, that even the most familiar objects have stories to tell, and that change is the only constant. Let your thoughts linger on the moon, its surface bathed in the soft glow of Earthlight. Picture its early days, a time of fire and chaos, when massive impacts and tidal forces shaped its destiny. Imagine the molten core, swirling and churning, generating a magnetic field that once enveloped the moon in a protective embrace. The moon's magnetic field is a reminder that even the quietest places have a history, that even the most familiar objects hold secrets waiting to be discovered. It challenges us to think beyond the limits of our understanding, to explore the mysteries of the cosmos, and to marvel at the beauty of the universe. Take a moment to reflect on the moon's magnetic field, a phenomenon that defies easy explanation. In its rise and fall, we find a symbol of the dynamic nature of the universe, a reminder that everything is connected, that everything is part of a larger story. The mystery of the moon's magnetic field is not just a scientific challenge, it is a journey into the heart of reality. It invites us to explore the deepest truths of the cosmos, to marvel at the beauty of the universe, and to wonder what other mysteries lie, waiting to be discovered. Let your imagination wander through the mysteries of the moon's magnetic field, a phenomenon that bridges the past and the present, the familiar and the unknown. In its strange and beautiful dance, we find a reflection of our own place in the cosmos, a reminder that we are all part of something greater, something infinite, something eternal. The mystery of the cosmic web. The universe is not a random scattering of stars and galaxies. Instead, it is a vast, intricate network, a cosmic tapestry woven by gravity over billions of years. This network, known as the cosmic web, is one of the most beautiful and mysterious structures in the cosmos. It is a web of galaxies, gas, and dark matter, stretching across the universe in filaments and nodes, with vast voids in between. The cosmic web is the skeleton of the universe, the framework that shapes its evolution and defines its structure. The story of the cosmic web begins with the Big Bang, the event that gave birth to the universe. In its earliest moments, the universe was a hot, dense soup of particles, almost perfectly uniform. But tiny fluctuations in density, imprinted by quantum processes, created the seeds of structure. Over billions of years, gravity amplified these fluctuations, pulling matter together into dense regions and leaving behind empty voids. The result is the cosmic web, a network of filaments and nodes that spans the observable universe. The filaments are long, thread-like structures made of galaxies, gas, and dark matter, while the nodes are dense clusters where filaments intersect. Between these structures lie vast voids, regions of space that are almost entirely empty. The cosmic web is not just a static structure, it is a dynamic, evolving system. Galaxies flow along the filaments, drawn toward the nodes by gravity. Gas and dark matter are constantly moving, shaping and reshaping the web over time. This movement is driven by the interplay of gravity, dark matter, and dark energy, the mysterious forces that govern the universe. Yet, despite its beauty and complexity, the cosmic web remains shrouded in mystery. One of the greatest challenges in studying it is its sheer scale. The filaments of the cosmic web can stretch for hundreds of millions of light-years, making them difficult to observe in their entirety. To map the cosmic web, astronomers use a variety of techniques. One approach is to observe the distribution of galaxies, using telescopes to survey large regions of the sky. By measuring the positions and distances of millions of galaxies, scientists can reconstruct the underlying structure of the cosmic web. Another approach is to study the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in the cosmic microwave background reveal the seeds of structure in the early universe, providing clues about how the cosmic web formed. Yet another technique is to observe the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars. These lines are caused by clouds of hydrogen gas along the line of sight, and they trace the distribution of matter in the cosmic web. These observations have revealed a universe that is far more structured and interconnected than we once thought. The cosmic web is not just a collection of isolated galaxies, it is a vast interconnected network, a tapestry of light and matter that spans the cosmos. But the cosmic web is more than just a scientific curiosity. It is also a window into the fundamental forces that shape the universe. The filaments and nodes of the cosmic web are shaped by gravity, the force that binds the cosmos together. The voids, on the other hand, are shaped by dark energy, the mysterious force that drives the accelerated expansion of the universe. The interplay of these forces creates the intricate structure of the cosmic web, a structure that is both beautiful and mysterious. It challenges our understanding of the universe, forcing us to rethink our assumptions about its origins and evolution. The cosmic web also has profound implications for our understanding of dark matter. Dark matter, which makes up about 85% of the matter in the universe, is invisible to telescopes, but its presence is revealed by its gravitational effects. The filaments and nodes of the cosmic web are thought to be dominated by dark matter, which provides the scaffolding for the visible structures we see. Yet despite its importance, dark matter remains one of the greatest mysteries in science. What is it made of? How does it interact with ordinary matter? These questions lie at the heart of the cosmic web, and answering them could revolutionize our understanding of the universe. The cosmic web also invites us to reflect on our place in the universe. We are part of this vast interconnected network, our galaxy just one thread in the cosmic tapestry. The filaments and nodes of the cosmic web are not just abstract structures. They are the framework of our existence, the stage on which the story of the universe unfolds. Let your thoughts linger on the cosmic web, a network of galaxies, gas, and dark matter that spans the universe. Picture the filaments, stretching across the cosmos like threads of light. Imagine the nodes, dense clusters of galaxies where the threads intersect, and between them, the voids, vast regions of emptiness that remind us of the scale and complexity of the universe. The cosmic web is a reminder that the universe is not just a collection of isolated objects, but a dynamic, interconnected whole. It challenges us to think beyond the limits of our intuition, to embrace the strange and beautiful truths of the cosmos, and to wonder what other mysteries lie, waiting to be discovered. Take a moment to reflect on the cosmic web, a structure that bridges the past and the present, the familiar and the unknown. In its intricate patterns, we find a symbol of the unity that underlies all of existence, a reminder that we are all part of something greater, something infinite, something eternal. The mystery of the cosmic web is not just a scientific challenge. It is a journey into the heart of reality. It invites us to explore the deepest truths of the universe, to marvel at the beauty of the cosmos, and to wonder what lies beyond the edge of our understanding. Let your imagination wander through the mysteries of the cosmic web, a structure that spans the universe and connects all things. In its strange and beautiful dance, we find a reflection of our own place in the cosmos, a reminder that we are all part of something greater, something infinite, something eternal. The mystery of the universe's missing baryons. The universe is a place of wonder and mystery, filled with galaxies, stars, and planets. Yet, despite its apparent richness, it holds a profound secret. A significant portion of its ordinary matter is missing. This missing matter, known as the missing baryon problem, is one of the most intriguing puzzles in modern cosmology. Baryons are particles that make up the ordinary matter we see around us: protons, neutrons, and electrons. They are the building blocks of atoms, the stuff of stars, planets, and life itself. According to the standard model of cosmology, baryons should account for about 5% of the universe's total mass and energy. Yet when astronomers tally up all the visible matter in the universe, stars, galaxies, gas, and dust, they find only about half of the expected amount. Where are the missing baryons? This question has puzzled scientists for decades, and the search for an answer has taken them to the farthest reaches of the cosmos. One possibility is that the missing baryons are hiding in the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. The cosmic web is made up of dark matter, which provides the gravitational scaffolding, and ordinary matter, which flows along the filaments and collects in the nodes. Much of this ordinary matter is in the form of warm, hot intergalactic medium, a diffuse gas that fills the space between galaxies. The warm, hot intergalactic medium is incredibly hot, with temperatures ranging from hundreds of thousands to millions of degrees, and it is so thin that it is almost invisible to telescopes. Detecting the warm, hot intergalactic medium is a formidable challenge, but astronomers have developed ingenious methods to find it. One approach is to look for the absorption of light from distant quasars, the bright cores of active galaxies. As the light passes through the warm, hot intergalactic medium, it is absorbed at specific wavelengths, creating a series of absorption lines in the quasar spectrum. These lines, known as the Lyman alpha forest, provide a map of the distribution of gas in the cosmic web. Another approach is to use X-ray telescopes, which can detect the faint glow of the warm-hot intergalactic medium as it emits X-rays. These observations have revealed vast reservoirs of hot gas in the filaments of the cosmic web, but they still account for only a fraction of the missing baryons. The search for the missing baryons has also taken astronomers to the outskirts of galaxy clusters, where the gas is denser and easier to detect. These regions, known as the intracluster medium, are filled with hot gas that emits X-rays. By studying the X-ray emission, astronomers can estimate the amount of baryonic matter in the clusters, but even this falls short of the expected total. So where are the rest of the missing baryons? One possibility is that they are in the form of dark baryons, matter that is not visible to our telescopes. This could include cold gas clouds, rogue planets, or even black holes. Another possibility is that the missing baryons are in the form of diffuse gas that is too faint or too spread out to detect. The mystery of the missing baryons also has implications for our understanding of the universe's evolution. According to the standard model of cosmology, the universe began with a hot, dense soup of particles, almost perfectly uniform. Over time, gravity amplified tiny fluctuations in density, pulling matter together into galaxies and galaxy clusters. But if a significant portion of the baryons are missing, it suggests that our understanding of this process is incomplete. It challenges us to rethink our assumptions about the distribution of matter in the universe and the forces that shape it. The missing baryons also invite us to reflect on the nature of the universe itself. The universe is not just a collection of stars and galaxies. It is a dynamic, evolving system, full of contrasts and surprises. The missing baryons are a reminder that even the most familiar objects have secrets waiting to be discovered. Let your thoughts linger on the missing baryons, the ordinary matter that is hidden in the vastness of space. Picture the cosmic web, a network of filaments and voids that spans the universe. Imagine the warm, hot intergalactic medium, the diffuse gas that fills the space between galaxies, and the faint glow of X-rays that reveal its presence. The missing baryons are a reminder that the universe is not just a collection of isolated objects, but a dynamic, interconnected whole. They challenge us to think beyond the limits of our understanding, to explore the mysteries of the cosmos, and to marvel at the beauty of the universe. Take a moment to reflect on the missing baryons, a mystery that bridges the past and the present, the familiar and the unknown. In their absence, we find a symbol of the vastness and complexity of the universe, a reminder that we are all part of something greater, something infinite, something eternal. The mystery of the missing baryons is not just a scientific challenge. It is a journey into the heart of reality. It invites us to explore the deepest truths of the universe, to marvel at the beauty of the cosmos, and to wonder what other mysteries lie waiting to be discovered. Let your imagination wander through the mysteries of the missing baryons, a puzzle that spans the universe and connects all things. In their strange and beautiful absence, we find a reflection of our own place in the cosmos, a reminder that we are all part of something greater, something infinite, something eternal. The mystery of the Cambrian explosion. The history of life on Earth is a story of gradual change, of species evolving over billions of years to fill every niche and corner of the planet. But there is one chapter in this story that stands out as extraordinary. a period of rapid and unprecedented transformation known as the Cambrian explosion. Around 540 million years ago, in a geological blink of an eye, life on Earth underwent a dramatic burst of diversification, giving rise to most of the major animal groups we see today. This event is one of the most profound mysteries in evolutionary biology, a puzzle that challenges our understanding of how life evolves. The Cambrian explosion marks the beginning of the Cambrian period, a time when life on Earth transitioned from simple, single-celled organisms to complex, multicellular animals. Before the Cambrian, life was mostly microbial, with a few exceptions like the enigmatic Ediacaran biota, soft-bodied organisms that left behind faint traces in the fossil record. But during the Cambrian, the fossil record suddenly explodes with a dazzling array of life forms: trilobites, arthropods, mollusks, and even the earliest ancestors of vertebrates. What caused this sudden burst of complexity? Why did life, after billions of years of relative simplicity, suddenly diversify into so many forms? These questions lie at the heart of the mystery of the Cambrian explosion, a mystery that has fascinated scientists for over a century. One of the most striking features of the Cambrian explosion is the rapid pace at which it occurred. In geological terms, it was almost instantaneous, lasting just 20 to 25 million years. To put this in perspective, the Earth is about 4.5 billion years old, and life has existed for at least 3.7 billion years. The Cambrian explosion represents less than 1% of life's history, yet it accounts for the emergence of most of the animal body plans we see today. This rapid diversification challenges the traditional view of evolution as a slow, gradual process. Instead, it suggests that under certain conditions, evolution can occur in sudden bursts, driven by a combination of genetic, environmental, and ecological factors. One possible explanation for the Cambrian explosion is the rise of predation. Before the Cambrian, life was mostly peaceful, with organisms feeding on organic matter in the water or on the seafloor. But during the Cambrian, the first predators appeared, armed with claws, jaws, and other tools for hunting. This shift in ecological dynamics may have triggered an evolutionary arms race, with prey species evolving new defenses and predators evolving new ways to overcome them. Another factor that may have contributed to the Cambrian explosion is the increase in atmospheric oxygen. Before the Cambrian, oxygen levels were relatively low, limiting the size and complexity of organisms. But around this time, oxygen levels began to rise, providing the energy needed to support larger, more active bodies. This increase in oxygen may have been driven by the evolution of photosynthetic organisms, which released oxygen as a byproduct of their metabolism. Yet another possibility is that the Cambrian explosion was driven by changes in the Earth's geology and climate. During this time, the continents were coming together to form the supercontinent Gondwana, creating new habitats and ecological niches. At the same time, the climate was warming and sea levels were rising, flooding vast areas of land and creating shallow marine environments where life could thrive. But while these factors may have set the stage for the Cambrian explosion, they do not fully explain why it happened when it did. One of the most intriguing ideas is that the explosion was driven by the evolution of developmental genes, the genetic toolkit that controls how organisms grow and develop. During the Cambrian, new genes and genetic pathways may have emerged, allowing organisms to evolve new body plans and structures. For example, the evolution of the Hox genes, which control the development of body segments, may have enabled the diversification of arthropods, the group that includes insects, spiders, and crustaceans. The Cambrian explosion also raises profound questions about the nature of evolution itself. Is evolution a slow, gradual process, or can it occur in sudden bursts? Are there certain conditions that trigger rapid diversification, or is it simply a matter of chance? These questions are not just scientific, they are also philosophical. They challenge us to think about the nature of life, about the forces that shape its evolution, and about our place in the grand tapestry of existence. Let your thoughts linger on the Cambrian explosion, a time when life on Earth underwent a dramatic transformation. Picture the ancient oceans, teeming with strange and wonderful creatures, trilobites scuttling across the sea floor, jellyfish drifting in the currents, and the first fish darting through the water. Imagine the evolutionary arms race, with predators and prey locked in a struggle for survival, driving the diversification of life. The Cambrian explosion is a reminder that life is not static, but dynamic, constantly evolving and adapting to new challenges. It challenges us to think beyond the limits of our understanding, to explore the mysteries of the cosmos, and to marvel at the beauty of the universe. Take a moment to reflect on the Cambrian explosion, a mystery that bridges the past and the present, the familiar and the unknown. In its sudden burst of complexity, we find a symbol of the dynamic nature of life, a reminder that everything is connected, that everything is part of a larger story. The mystery of the Cambrian explosion is not just a scientific challenge, it is a journey into the heart of reality. It invites us to explore the deepest truths of the universe, to marvel at the beauty of the cosmos, and to wonder what other mysteries lie waiting to be discovered. Let your imagination wander through the mysteries of the Cambrian explosion, a story that spans millions of years and connects us to the very beginnings of complex life. In its strange and beautiful dance, we find a reflection of our own place in the cosmos, a reminder that we are all part of something greater, something infinite, something eternal. The puzzle of the pioneer anomaly. In the vast expanse of space, where distances are measured in light years and time stretches across billions of years, even the smallest anomalies can reveal profound mysteries. One such mystery is the Pioneer Anomaly, a tiny but persistent deviation in the trajectories of the Pioneer 10 and Pioneer 11 spacecraft that has puzzled scientists for decades. Launched in the early 1970s, the Pioneer missions were among the first to explore the outer reaches of the solar system. Pioneer 10, launched in 1972, was the first spacecraft to travel through the asteroid belt and make a close flyby of Jupiter. Pioneer 11, launched a year later, followed a similar path before continuing on to Saturn. Both spacecraft provided invaluable data about the gas giants and their moons, revolutionizing our understanding of the outer solar system. But as the pioneers ventured farther from the Sun, something unexpected happened. Their trajectories began to deviate slightly from what was predicted by the laws of gravity. This deviation, known as the Pioneer Anomaly, was tiny, just a fraction of a millimeter per second squared, but it was consistent and unexplained. At first, scientists assumed the anomaly was due to some mundane cause, such as a fuel leak or a technical glitch. But as the years passed and the anomaly persisted, it became clear that something more fundamental was at play. The Pioneer Anomaly was not just a quirk of the spacecraft. It was a mystery that challenged our understanding of gravity and the laws of physics. The Pioneer Anomaly became one of the most intriguing puzzles in space exploration, sparking a decades-long search for an explanation. Scientists proposed a wide range of theories, from the mundane to the exotic. Some suggested that the anomaly was caused by the uneven emission of heat from the spacecraft's radioisotope thermoelectric generators, which could create a tiny but measurable thrust. Others proposed that it was due to the gravitational pull of unknown objects in the outer solar system, such as a hidden planet or a cloud of dark matter. Yet another possibility was that the anomaly was evidence of new physics, a sign that our understanding of gravity was incomplete. According to Einstein's theory of general relativity, gravity is the curvature of space-time caused by mass and energy. But some scientists suggested that the Pioneer Anomaly could be evidence of a modification to general relativity, such as a fifth force or a variation in the gravitational constant. The search for an explanation was complicated by the fact that the Pioneer spacecraft were not designed to measure such tiny deviations. Their instruments were built to study the planets, not to test the laws of physics. As a result, scientists had to rely on indirect methods, such as analyzing the Doppler shift of the spacecraft's radio signals, to detect the anomaly. Despite these challenges, the Pioneer Anomaly captured the imagination of scientists and the public alike. It was a reminder that even in the age of space exploration, there are still mysteries waiting to be solved, still questions that challenge our understanding of the universe. In 2012, after decades of analysis, a team of scientists announced that they had solved the mystery. The anomaly, they concluded, was caused by the uneven emission of heat from the spacecraft's power sources. As the pioneers traveled through space, they emitted heat in all directions, but the heat emitted from the back of the spacecraft was slightly greater than the heat emitted from the front. This created a tiny but measurable thrust, pushing the spacecraft off course. The explanation was elegant and straightforward, but it left some scientists unsatisfied. While the heat emission theory accounted for most of the anomaly, it did not explain all of it. There was still a small but significant discrepancy, a hint that there might be more to the story. The Pioneer anomaly also raised broader questions about the nature of gravity and the laws of physics. If even a tiny deviation in the trajectory of a spacecraft can reveal new insights, what other mysteries might be hidden in the cosmos? Could there be other anomalies, other deviations, that point to new physics or undiscovered forces? These questions are not just scientific, they are also philosophical. They challenge us to think about the nature of reality, about the forces that shape the universe, and about our place in the grand tapestry of existence. Let your thoughts linger on the Pioneer anomaly, a tiny but persistent deviation in the trajectories of two spacecraft. Picture the pioneers, their golden records carrying messages from Earth, venturing into the unknown reaches of the solar system. Imagine the scientists poring over decades of data, searching for an explanation to this cosmic puzzle. The Pioneer anomaly is a reminder that the universe is full of surprises, that even the smallest deviations can reveal profound truths. It challenges us to think beyond the limits of our understanding, to explore the mysteries of the cosmos, and to marvel at the beauty of the universe. Take a moment to reflect on the Pioneer anomaly, a mystery that bridges the past and the present, the familiar and the unknown. In its tiny deviation, we find a symbol of the vastness and complexity of the universe, a reminder that we are all part of something greater, something infinite, something eternal. The mystery of the Pioneer anomaly is not just a scientific challenge, it is a journey into the heart of reality. It invites us to explore the deepest truths of the universe, to marvel at the beauty of the cosmos, and to wonder what other mysteries lie waiting to be discovered. Let your imagination wander through the mysteries of the Pioneer anomaly, a puzzle that spans the solar system and connects us to the very beginnings of space exploration. In its strange and beautiful dance, we find a reflection of our own place in the cosmos, a reminder that we are all part of something greater, something infinite, something eternal. The mystery of the ghost particles, neutrinos. Neutrinos. These tiny, almost massless subatomic particles are among the most abundant particles in the universe, yet they are also incredibly elusive. They've earned the nickname ghost particles because they interact so weakly with matter that they can pass through planets, stars, and even entire galaxies virtually unimpeded. Trillions of neutrinos are passing through your body every second, and you don't even notice them. This very characteristic that makes them so difficult to detect also makes them incredibly interesting and holds the key to some of the biggest mysteries in physics. Neutrinos are produced in a variety of nuclear reactions, such as those that power stars, as well as in radioactive decay and other processes. They come in three flavors: electron neutrinos, muon neutrinos, and tau neutrinos. Each flavor is associated with a corresponding charged lepton, electron, muon, and tau, respectively. For many years, it was thought that neutrinos were massless particles, traveling at the speed of light. This seemed to fit with the standard model of particle physics, our current best theory, describing the fundamental forces and particles of nature. However, experiments began to reveal a surprising and profound mystery. Neutrinos have mass. The evidence for neutrino mass came from observations of neutrino oscillations. This phenomenon, first predicted theoretically, involves neutrinos changing from one flavor to another as they travel. Imagine a beam of muon neutrinos traveling through space. As they journey, some of those muon neutrinos will spontaneously transform into electron neutrinos or tau neutrinos, and vice versa. This oscillation between flavors is only possible if neutrinos have mass. If they were massless, they would travel at the speed of light, and time would effectively stop for them, preventing any such transformation. This is a purely quantum mechanical effect, a testament to the strange and counterintuitive nature of the subatomic world. It's as if a chameleon, while sprinting at nearly the speed of light, could spontaneously change its colors mid-stride. The discovery of neutrino oscillations, and therefore neutrino mass, was a groundbreaking moment in particle physics. It was the first clear evidence of physics beyond the standard model, indicating that our understanding of the universe, at its most fundamental level, was incomplete. It opened up a new area of research, focused on understanding the properties of neutrinos and their role in the universe. It was a bit like discovering a new continent on a map you thought was complete, exciting, and full of potential for new discoveries. However, the fact that neutrinos have mass raises more questions than it answers. The standard model, in its original form, couldn't accommodate massive neutrinos. So physicists had to modify the model to include neutrino masses, but the masses of neutrinos are incredibly tiny, much smaller than the masses of other fundamental particles like quarks or even the electron. Why are they so light? This is a major puzzle. One leading theory suggests that neutrinos acquire their mass through a mechanism called the seesaw mechanism, which involves the existence of very heavy, hypothetical particles called right-handed neutrinos. These right-handed neutrinos, if they exist, would be much heavier than any other known particle. They would interact with the Higgs field, the field that gives other particles their mass, and this interaction would give rise to the tiny masses of the left-handed neutrinos that we observe. The seesaw mechanism is an elegant idea, but it requires the existence of these heavy right-handed neutrinos, which we have yet to detect directly. Their existence is inferred, if they exist at all, through the tiny masses of the neutrinos we can detect. Another mystery surrounding neutrinos is their absolute mass scale. While experiments have measured the differences between the masses of the three neutrino flavors, they haven't yet been able to determine the absolute mass of each neutrino. This is a crucial piece of information for understanding the role of neutrinos in cosmology and particle physics. Imagine knowing the relative heights of three mountains, but not knowing the height of the lowest one above sea level. You'd know how much taller one is than the other, but not their actual elevations. That's the challenge with neutrino mass. Scientists are trying to determine the absolute neutrino mass scale through various experiments, including those that study radioactive decay and those that look for the effects of neutrinos on the cosmic microwave background radiation. These experiments are incredibly delicate and require exquisite precision. Neutrinos also play a crucial role in nuclear reactions within stars. They are produced in vast numbers in the cores of stars, carrying away energy that helps to regulate the nuclear fusion process. Without neutrinos, stars would burn much hotter and faster, and the universe as we know it would be very different. Our sun, for example, is a giant neutrino factory. The energy that reaches us as sunlight is a product of nuclear fusion in the sun's core, a process that also floods space with neutrinos. These neutrinos stream outwards, unimpeded, carrying vital information about the conditions deep within the sun. Neutrinos are also thought to play a role in the formation of heavy elements in supernovae. These exploding stars are some of the most powerful events in the universe, and they are responsible for creating many of the elements that make up planets and even life itself. The neutrinos emitted in supernovae carry valuable information about the inner workings of these stellar explosions. By studying these neutrinos, scientists can gain insights into the processes that create heavy elements and seed the universe with them. It's like getting a glimpse inside a cosmic forge. One of the most intriguing aspects of neutrinos is their connection to the matter-antimatter asymmetry in the universe. According to our current understanding of physics, the Big Bang should have produced equal amounts of matter and antimatter. However, we observe a universe dominated by matter. Why is there so much more matter than antimatter? This is one of the biggest unsolved problems in physics. Neutrinos could play a crucial role in explaining this asymmetry. One theory suggests that neutrinos and antineutrinos behave slightly differently, a phenomenon called leptogenesis. This difference in behavior could have led to the creation of more matter than antimatter in the early universe. This is a very active area of research, with scientists exploring various ways in which neutrinos could have contributed to the matter-antimatter balance. The study of neutrinos is a vibrant and active field of research. Scientists are constantly developing new and more sensitive experiments to probe the properties of these elusive particles. They're trying to measure their masses, their mixing angles, and their other fundamental properties. These experiments often involve huge detectors buried deep underground or underwater, shielded from cosmic rays and other background noise. They are also searching for new types of neutrinos, such as sterile neutrinos, which are hypothetical particles that interact even more weakly than the known neutrinos. These sterile neutrinos, if they exist, could be a key to unlocking further secrets about the universe. Understanding the mysteries of neutrinos is one of the key challenges in modern physics. These ghostly particles hold the potential to unlock new secrets about the universe, from the fundamental laws of nature to the origin of matter itself. Their study exemplifies how even the smallest, seemingly insignificant particles can hold the biggest clues to understanding the cosmos. They are, in a very real sense, messengers from the most extreme environments in the universe, offering us a glimpse into processes that would otherwise be invisible. The mystery of fast radio bursts. Imagine the universe as a vast cosmic radio station, constantly broadcasting a symphony of signals across the electromagnetic spectrum. Among these cosmic broadcasts, there exists a particularly enigmatic phenomenon: fast radio bursts, or FRBs. These are incredibly intense bursts of radio waves that flash across the sky for just a few milliseconds, a blink of an eye in cosmic timescales. Despite their fleeting nature, these bursts pack an incredible punch, releasing as much energy in a millisecond as the sun does in an entire year. Their brief but brilliant appearance has captivated astronomers and ignited a global hunt to understand their origin. The first FRB was discovered serendipitously in 2007 by astronomers sifting through archival data from the Parkes Radio Telescope in Australia. It was a single powerful burst unlike anything seen before. Imagine searching through old photos and suddenly finding a picture of something completely unexpected and unexplainable. That's what it was like. It was named the Lorimer Burst, after the astronomer who first identified it, and it remained a unique event for several years. Scientists were unsure if it was a one-off fluke or a sign of a new, previously unknown, cosmic phenomenon. It was a bit like finding a single, unusually bright star in the night sky and wondering if it was a sign of something more significant. As more telescopes joined the search, more FRBs were discovered, confirming that these bursts were not a rare occurrence but a genuine astrophysical phenomenon. The bursts are detected across the sky, suggesting they originate from vast distances, likely from other galaxies. This immense distance implies that the sources of FRBs must be incredibly powerful. Think of it like hearing a firecracker go off on the other side of the world. It must have been a very big firecracker. The sheer energy released in such a short time is what makes FRBs so remarkable and so challenging to explain. One of the biggest mysteries surrounding FRBs is their origin. What kind of cosmic objects could produce such powerful bursts of radio waves in such a short amount of time? Several theories have been proposed, ranging from exotic objects like magnetars to more speculative ideas involving axions, cosmic strings, and even, though highly unlikely, extraterrestrial intelligence. The sheer variety of proposed explanations highlights the difficulty of the problem and the excitement surrounding the search for answers. Magnetars, which are neutron stars with incredibly strong magnetic fields, are currently the leading candidates. Neutron stars are the collapsed cores of massive stars that have reached the end of their lives. They are incredibly dense, packing the mass of the Sun into a sphere only about 20 kilometers across. Magnetars are even more extreme, with magnetic fields 1,000 trillion times stronger than Earth's. These extreme magnetic fields could potentially generate the powerful bursts of radio waves we observe as FRBs. Imagine a giant, incredibly powerful magnet spinning rapidly and occasionally emitting bursts of energy. The intense magnetic fields could accelerate charged particles to incredibly high energies, which could then produce the radio waves. However, the exact mechanism by which this happens is still a matter of debate. Another possibility is that FRBs are produced by some kind of interaction between neutron stars and other objects, such as black holes or other neutron stars. These interactions could trigger powerful flares or other events that produce radio waves. Think of it like two colliding sparks, creating a bigger, brighter flash. For example, a neutron star orbiting a black hole could periodically shed material, which could then interact with the black hole's magnetic field to produce an FRB. Some more exotic theories involve hypothetical objects like blitzars, or even superconducting cosmic strings. These are highly speculative ideas, but they illustrate the wide range of possibilities that scientists are considering. A blitzar, for example, is a theoretical type of neutron star that collapses into a black hole. The collapse could potentially generate a burst of radio waves. Cosmic strings are hypothetical, one-dimensional topological defects in space-time that are thought to have formed in the early universe. Their decay could also potentially produce FRBs. One of the most intriguing aspects of FRBs is that some of them repeat. While most FRBs are single, isolated events, some have been observed to emit multiple bursts, sometimes in a regular pattern. These repeating FRBs are particularly interesting because they provide more opportunities to study the bursts and try to understand their origin. The fact that they repeat suggests that the source is not destroyed in the process of producing the burst, as would be the case with a cataclysmic event like a supernova. It also allows astronomers to observe these sources over longer periods, looking for patterns or changes in their behavior. The discovery of repeating FRBs has also raised the possibility that they could be produced by some kind of periodic process, like the rotation of a neutron star or the orbital motion of two objects in a binary system. Imagine a lighthouse emitting a beam of light that sweeps across the sky. If the Earth happens to be in the path of the beam, we would see a flash of light every time the lighthouse rotates. Similarly, repeating FRBs could be produced by a rotating object emitting a beam of radio waves. The periodic nature of the bursts could then be linked to the rotation period of the source. The study of FRBs is still in its early stages, but it is a rapidly evolving field. New telescopes, like the Canadian Hydrogen Intensity Mapping Experiment, (CHIME), and the Square Kilometre Array, (SKA), are being built specifically to search for and study FRBs, and astronomers are using a variety of techniques to try to understand their origin. One of the key challenges is to pinpoint the exact location of FRBs so that they can be studied at other wavelengths, such as optical or X-ray. This would provide valuable clues about the nature of the sources. Imagine trying to find the source of a sound without knowing where it's coming from. Pinpointing the location is the first step to understanding what's making the sound. The mystery of FRBs is a reminder of how much we still don't know about the universe. These fleeting bursts of radio waves are a cosmic puzzle, challenging our current understanding of astrophysics and pushing us to explore new ideas. They are a testament to the dynamic and ever-changing nature of the universe, and they offer a tantalizing glimpse into some of the most extreme and enigmatic objects in the cosmos. As we continue to observe and study these mysterious bursts, we can hope to unlock their secrets and gain a deeper understanding of the universe we inhabit. The search for the origin of FRBs is a journey into the unknown, a quest to unravel one of the universe's most captivating enigmas. It's a detective story on a cosmic scale, with FRBs as the clues and astronomers as the detectives. The mystery of animal navigation. Imagine a tiny hummingbird migrating thousands of miles, navigating across continents to reach its specific breeding grounds. Or picture a sea turtle, born on a beach, swimming across vast oceans, only to return to that very same beach years later to lay her own eggs. These incredible journeys are just a few examples of the remarkable navigational abilities of animals. How do they do it? How do they find their way across vast distances, often without any visible landmarks? The mystery of animal navigation is a complex and fascinating puzzle, one that has intrigued scientists for centuries. Animal navigation encompasses a wide range of behaviors, from simple orientation, knowing which way is up or down, to complex navigation, knowing how to reach a specific destination. Animals use a variety of cues to navigate, including the sun, the stars, the Earth's magnetic field, smells, and even polarized light. The specific cues used by an animal depend on its species, its environment, and the type of journey it is undertaking. One of the most well-known examples of animal navigation is the migration of birds. Many bird species undertake long migrations, traveling thousands of miles between their breeding and wintering grounds. These migrations can be incredibly challenging, requiring birds to navigate across vast distances, often over unfamiliar terrain. How do they do it? Birds use a combination of cues, including the sun, the stars, and the Earth's magnetic field. During the day, they can use the position of the sun to orient themselves. They have an internal clock that compensates for the sun's movement across the sky, allowing them to maintain a constant heading. At night, they can use the stars to navigate. They can recognize constellations and use them as celestial landmarks. Imagine a bird flying at night, using the pattern of stars like a map in the sky. Birds also have a remarkable ability to sense the Earth's magnetic field. They have tiny crystals of magnetite in their beaks and other parts of their bodies that allow them to detect the direction and intensity of the magnetic field. This magnetic sense acts like an internal compass, providing them with a sense of direction even when they can't see the sun or the stars. Think of it like having a built-in GPS that relies on the Earth's magnetic field instead of satellites. Sea turtles are another example of animals with incredible navigational abilities. These marine reptiles are born on beaches, then swim out into the ocean, where they spend several years feeding and growing. When it's time to reproduce, they return to the very same beach where they were born, often after traveling thousands of miles across the ocean. How do they manage this feat? Sea turtles also use the Earth's magnetic field to navigate. They imprint on the magnetic field of their natal beach as hatchlings, and they use this magnetic signature to find their way back years later. It's like the beach has its own unique magnetic address that the turtles can remember. Salmon also exhibit remarkable homing behavior. These fish are born in freshwater streams, then migrate to the ocean, where they spend several years feeding and growing. When it's time to reproduce, they return to the very same stream where they were born, often swimming thousands of miles upstream. Salmon use their sense of smell to navigate back to their natal stream. Each stream has its own unique chemical signature, and salmon can recognize this signature and follow it upstream. It's like following a scent trail through the water. Insects, too, possess impressive navigational skills. Honeybees, for example, can navigate back to their hive after foraging for food miles away. They use a combination of cues, including the sun, landmarks, and polarized light. Polarized light is light that has been filtered so that its waves vibrate in a particular direction. Bees can detect the polarization of sunlight, which provides them with information about the sun's position even on cloudy days. They also create a map of their surroundings, remembering landmarks and using them to guide their way. It's like bees create a mental map of their environment to help them navigate. The study of animal navigation is a complex and challenging field. Scientists are still trying to understand the exact mechanisms by which animals navigate. They are using a variety of techniques, including tracking animals with GPS devices, studying their behavior in laboratory settings, and examining their brains to identify the neural circuits involved in navigation. One of the key questions that scientists are trying to answer is how animals process and integrate the different navigational cues they receive. How do they decide which cue to follow when different cues provide conflicting information? Imagine a bird trying to navigate using both the sun and the Earth's magnetic field, but the two cues point in different directions. How does the bird decide which way to go? Another area of research is the role of learning and memory in animal navigation. How do animals learn to navigate? Do they inherit their navigational abilities, or do they learn them through experience? Studies have shown that both genetic predisposition and experience play a role in animal navigation. Some species have an innate ability to navigate, while others learn to navigate through trial and error. The mystery of animal navigation is not only fascinating from a scientific perspective, but it also has important implications for conservation. Many animal populations are facing threats from habitat loss and climate change. Understanding how animals navigate is crucial for developing effective conservation strategies. If we know how animals find their way, we can better protect their migration routes and breeding grounds. The remarkable navigational abilities of animals are a testament to their adaptability and their connection to their environment. They remind us of the intricate and complex web of life on Earth and the many mysteries that still remain to be unraveled. From the smallest insect to the largest whale, animals possess an innate ability to find their way, a skill that is essential for their survival and that continues to inspire and amaze us. The nature of gravity, a cosmic puzzle. Gravity. It's the force that keeps our feet on the ground, the planets in orbit around the sun, and galaxies bound together in vast cosmic structures. It's a force we experience every moment of our lives, yet its fundamental nature remains one of the greatest unsolved mysteries in physics. We have a very good understanding of how gravity works, thanks to Albert Einstein's theory of general relativity. But the why, the underlying mechanism that gives rise to this ubiquitous force, continues to elude us. Imagine dropping a ball. It falls to the ground because of gravity. That's something we experience every day. But what is gravity, really? Newton's law of universal gravitation, formulated in the 17th century, gave us a way to describe this force mathematically. It said that everything with mass pulls on everything else with mass. The bigger the objects, the stronger the pull, and the farther apart they are, the weaker the pull. This law was incredibly useful. It allowed scientists to predict the movements of planets, comets, and even falling apples. Think of it like a recipe for how gravity behaves. It tells you what ingredients, mass and distance, to use, and what the result, the gravitational force, will be. However, Newton's law was incomplete. It described what gravity did, but not how it did it. It was like having the recipe but not understanding the underlying chemistry of why the ingredients combine the way they do. It was a mystery how this pull could happen across empty space. How could the sun, millions of miles away, exert a force on Earth? Then came Einstein, with his theory of general relativity, published in 1915. This changed everything. Einstein said that gravity isn't a force at all. Instead, it's a curvature of space-time caused by mass and energy. Imagine a bowling ball placed on a trampoline. The bowling ball creates a dip, a curve in the fabric of the trampoline. Now, if you roll a marble nearby, it won't travel in a straight line. It will curve around the bowling ball, following the dip in the trampoline. That's how gravity works. According to Einstein, massive objects, like planets and stars, warp the fabric of space-time, creating curves that other objects follow. We perceive this curving motion as the force of gravity. So, the Earth orbits the Sun not because the Sun is pulling on it, but because the Sun is warping space-time, and the Earth is simply following the curves. General relativity is incredibly accurate. It explains things that Newton's theory couldn't, like why light bends as it passes near the Sun. Imagine shining a flashlight past the Sun. The light, even though it has no mass, will bend slightly because it's traveling through the curved space-time around the Sun. This bending of light has been observed and confirms Einstein's theory. But here's the catch. General relativity, which describes gravity on large scales, is incompatible with quantum mechanics, which describes the world at the smallest scales, the world of atoms and subatomic particles. Quantum mechanics says that energy and momentum come in tiny packets, like little bundles. Think of it like popcorn. You can have 1 kernel, 2 kernels, 3 kernels, but not 1.5 kernels. Everything is quantized. General relativity, on the other hand, describes space-time as smooth and continuous, like a flowing river. These two theories are fundamentally different, and physicists have been struggling for decades to find a way to reconcile them. This incompatibility becomes a real problem when we try to understand gravity at extremely small scales or in extreme situations, like inside a black hole. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. At the center of a black hole is a singularity, a point of infinite density. Our current understanding of physics breaks down at this point. We need a theory of quantum gravity to understand what happens inside a black hole. Several theories have been proposed to try to unify general relativity and quantum mechanics. One of the most popular is string theory. String theory says that fundamental particles aren't point-like objects, but tiny, vibrating strings. Think of it like the strings on a guitar. Different vibrations create different notes, and in string theory, different vibrations create different particles. String theory also suggests that there are extra dimensions of space, curled up so small that we can't see them. Another approach is loop quantum gravity. This theory says that space-time itself is made up of tiny loops, like a fabric woven from incredibly small threads. Loop quantum gravity doesn't require extra dimensions, but it fundamentally changes our understanding of space and time at the smallest scales. Neither string theory nor loop quantum gravity has been definitively proven. They are both complex mathematical frameworks, and physicists are still working to develop them and test their predictions. Scientists are also looking for clues in other areas, like the early universe and the cosmic microwave background radiation. The very early universe was a very hot and dense place, where quantum effects were likely very important. The cosmic microwave background is like a snapshot of the early universe, and scientists are studying it carefully to look for signs of quantum gravity. The quest to understand the nature of gravity is one of the most important challenges in modern physics. It's a journey to understand the fundamental building blocks of the universe and the forces that shape it. It's a journey that could lead to a revolution in our understanding of space, time, and everything in between. The nature of memory. A labyrinth of the mind. Memory. It's the cornerstone of our identity, the repository of our experiences, and the foundation upon which we build our understanding of the world. It allows us to learn from the past, navigate the present, and imagine the future. From the mundane task of remembering where we left our keys to the profound ability to recall cherished moments with loved ones, memory shapes our lives in countless ways. Yet despite its fundamental importance, the nature of memory remains a complex and fascinating puzzle. How do we encode experiences into lasting memories? Where are these memories stored in the brain? And how do we retrieve them? Sometimes effortlessly, sometimes with great difficulty. Imagine trying to remember a specific event, like your first day at school. A flood of images, sounds, and emotions might come rushing back. The crisp smell of new crayons, the nervous chatter of classmates, the towering figure of your teacher. How is it possible for the brain to conjure up such a rich tapestry of sensory details from a single moment in time? This is just one of the many mysteries surrounding memory. Memory is not a single entity, but rather a collection of different systems, each serving a distinct purpose. One crucial distinction is between sensory memory, short-term memory, and long-term memory. Sensory memory is the briefest form of memory, lasting only a few seconds. It's the initial impression of sensory information, like the fleeting afterimage you see when you look at a bright light. If the information in sensory memory is deemed important, it is transferred to short-term memory. Short-term memory is like the brain's temporary notepad. It holds information for a short period, typically a few seconds to a minute, allowing us to perform tasks like remembering a phone number before dialing it. Short-term memory has a limited capacity, typically around 7 items. Try to remember a string of 10 random digits, and you'll likely find it challenging. This limitation is why we often chunk information into smaller, more manageable units. Instead of remembering 19842023, we might remember 1984 and 2023. Information in short-term memory can be further encoded and transferred to long-term memory, which is the brain's vast storage system for information that can last from minutes to a lifetime. Long-term memory is like the brain's library, containing a vast collection of knowledge, experiences, and skills. It is generally divided into 2 main categories: explicit, or declarative, memory and implicit, or non-declarative memory. Explicit memory refers to memories that can be consciously recalled and described, such as facts, events, and personal experiences. It's the kind of memory you use when you're taking a test or telling a story. Explicit memory is further divided into episodic memory, memories of specific events, and semantic memory, general knowledge about the world. Episodic memory is like a mental diary, recording the details of our lives. Semantic memory, on the other hand, is like an encyclopedia, containing facts, concepts, and general knowledge. Implicit memory, also known as non-declarative memory, refers to memories that are expressed through performance rather than conscious recall. It includes skills, habits, and learned associations. Riding a bicycle, playing a musical instrument, and even simple reflexes like blinking are examples of implicit memory. You don't consciously recall the steps involved in riding a bike, but you can still do it effortlessly. Implicit memory is often further divided into procedural memory, skills and habits, priming, influencing responses to stimuli, and classical conditioning, learned associations. The brain regions involved in memory are complex and interconnected. The hippocampus, a seahorse-shaped structure in the brain, plays a crucial role in forming new explicit memories, particularly episodic memories. It acts like a temporary storage site, consolidating memories before they are transferred to other parts of the brain for long-term storage. Imagine the hippocampus as a librarian, cataloging and organizing new books before placing them on the shelves. Damage to the hippocampus can result in difficulty forming new memories, a condition known as anterograde amnesia. The amygdala, a small almond-shaped structure near the hippocampus, is involved in processing emotional memories. It plays a key role in encoding the emotional intensity of experiences, which can enhance memory for emotionally arousing events. Think of how vividly you can remember a moment of intense joy or fear. The amygdala helps to create these strong emotional memories. The cerebral cortex, the outer layer of the brain, is thought to be involved in the long-term storage of memories. Different parts of the cortex are specialized for processing different types of sensory information, and these regions are also thought to be involved in storing memories related to those senses. For example, visual memories might be stored in the visual cortex, while auditory memories might be stored in the auditory cortex. The cerebellum, a structure at the back of the brain, is involved in procedural memory, particularly motor skills and habits. It plays a key role in learning and coordinating movements, allowing us to perform complex actions without conscious effort. While we have made significant progress in understanding the brain regions and processes involved in memory, many mysteries remain. How are memories encoded at the cellular level? What are the specific changes in brain circuitry that underlie learning and memory formation? How are memories retrieved from long-term storage, and why do we sometimes forget things? Forgetting is a natural part of memory. Some forgetting is due to encoding failure, meaning that the information was never properly stored in the first place. Other forgetting is due to retrieval failure, meaning that the information is stored, but we can't access it. Interference from other memories can also contribute to forgetting. Imagine trying to remember a phone number that is very similar to another phone number you know. The two memories might interfere with each other, making it difficult to recall the correct number. The study of memory is an ongoing journey, a quest to understand one of the most fundamental aspects of human cognition. Unraveling the mysteries of memory not only sheds light on how we learn and remember, but also has implications for understanding and treating memory disorders, such as Alzheimer's disease. By continuing to explore the labyrinth of the mind, we can gain deeper insights into the nature of memory and its profound impact on our lives. From the smallest quantum entanglement to the vastness of the multiverse, these unsolved mysteries remind us how much we still have to learn about the universe and our place within it. Thank you for joining us on this journey. May these stories of curiosity and mystery inspire you.